Okay, thank you very much, everyone. Welcome to the course on containers, CI/CD, continuous integration, continuous delivery and deployment, and benchmarking. So we are 3 days all together on this subjects. To start, first, I would like to make some recalling here a few things regarding the course. So three main components for the course. The objective at the end of the course is that you will be able to learn to containerize some HPC application, build it, deliver it, and then deploy it on machines such as Carolina. But to do so, we will need CI/CD workflows. So we'll study two settings, GitHub and GitLab, in order to do that. And we'll be able to deploy through these workflows to do the whole framework from building to deploying automatically from these systems. And finally, we'll see tools that we have developed here in Strasbourg in order to help or to automate benchmarking and report of benchmarks. So that would be the last tomorrow and the last day.
Morning, everyone. I am Javier Cladellas. I work as a research engineer in the Semosis team, and I'm the lead developer of FieldPP benchmarking, which is a tool to facilitate benchmarking in HPC systems. So I will be the tutor for days 1 and 3 for these trainings.
Hello, can you hear me?
Yes.
Yes, okay. So yes, as Christoph mentioned, I'm also from Hidalgo too, and I will be responsible for the GitLab training part. So basically, I will try to take what the Strasbourg colleagues teach you about containerization and CI/CD workflows through GitHub Actions and show how it can be done through GitLab and maybe the differences or what you have to take care of, security considerations and things like this. Yeah.
Thank you, Samir. Vincent, my colleague, one of my colleagues from Strasbourg.
Good morning. My name is Vincent Chaban. I am a research engineer at Semosis. I work with Christophe and Ravir, and my work, I am mainly a developer in some application in scientific computing and HPC.
Thank you, Vincent. Okay, then let's start. So how we organize things, we have some lectures, basically an hour and a half, where we introduce some of the key concepts. And then we can have some discussions. And those lectures are then followed by hands-on session with the, as I said at the beginning, the objective to be able to build your application up to deploying your application using CI/CD and containers, and also benchmark your application. So the objective is really to be able for you to do all this in an automated manner from scratch to the end. In order to handle the questions and answers, we have set up two ways. First, you have GitHub discussions. GitHub discussions here. You have the Q&A. You can start a discussion. This is part of the course. So if you are interested in the content, it's available here in this GitHub repository. So by having those questions here, they will stay and we can answer This is basically a forum. We can turn some of the questions into also GitHub issues. This is quite nice. So don't hesitate to use this tool. Then I need to find my course again. Yes. The other medium for discussion is actually Slack. So if you click on the link, you get an invitation to join Slack. So I will use it in the browser. So you can have it in the browser or download the application. It's available on cell phones up to laptops or desktop. Yeah. And so here, as you can see, the team is already there and waiting for your questions. So this is part of the Hidalgo 2 workspace, but here you have the ground to ask questions. The thing is that if you go back, let's say in 3-4 weeks, the messages here will have disappeared because we are running on a free version of Slack. So the messages after 30,000 or something, or 10,000, I don't remember exactly the number, but after some time, the messages disappear. So if you want to have a more something that is archived, do use the GitHub discussion system. Okay, so we will use Carolina. So we will use actually two systems in order to compile and deploy our courses, our hands-on session. And especially we will use Carolina because this is one of the objectives, to be able to deploy some compilation, for example, or some packaging or some computation on the system. So as you know, the project ID is this one. I've already put it in some of the scripts so that you don't have to enter it again, but feel free to play with this. So we'll be using GitLab and GitHub. What actually here we'll be using GitHub runners for some of the exercises. We'll see again. And so we will use also for uniformity and consistency, we will use GitHub Classroom in order to help create the repositories for each of you so that you have your own environment. And you will be able to use directly in your browser the VS Code. Of course, you are not obliged to. You can absolutely use VS Code. However, know that we have set up the environment so that you can have access to the tools for the course. So the software is already installed in the environment. And so there are no installation to be made at all. So the tools are there. And so that will be easier for us in order to guide you. The way we configured it is totally open. Everything is available for you to look at if you are interested. It's all in the repositories. So this morning, we are going to start with an overview for containerization. Then we'll do a break at 10:45. So we are right on time. Thank you so much for the quick presentation. We are now 36 in, so probably we missed some presentation of a few people. So we'll see at some point, but so 36 today to start with. So let's go with the first presentation. So first, containers. This is what we are going to do. Containers, they can, of course, be considered as or compared with virtualization systems. So I think it's important to understand the difference with virtualization technology. Then, of course, we want to understand how it helps for HPC workloads. We will see actually two technologies, Docker and Apptainer. You could consider Podman. In fact, Podman follows exactly the same interface as Docker, so it could be an exact replacement of Docker. And actually, you can find some tutorials online where people fake Docker by using Podman and replace or create an alias of Docker using Podman, and they actually replicate what is being done. So you can use also Podman if you like. We will not demonstrate it. We don't have the time, but you can see it as a replacement for Docker if you like, with a few changes. Okay, so but to start, maybe I think it might be interesting to understand why we are here, why I'm doing this presentation, why my colleagues are here today to make this course. Why are we, I hope, relevant to make this course? So I'm leading the Semosis Center. This is a center for modeling and simulation in Strasbourg. And we work with companies, we work with scientists in other disciplines, with research infrastructures, with big companies, with small companies. And one of the core tool that we developed is finite element software. Actually, it's much more than that now. It's really a framework for scientific and high-performance computing. It's called Fil++. Fil++ initially stand for finite element embedded language in C++. So the plus plus is about C++. So we'll do a little bit of C++ for the application background, but it's a very simple application. But here, I would like to use Fil++ as an example of why what we are going to do for the next 3 days, from containers to CI/CD and benchmarking, is absolutely crucial for such a software. Fil++ is a sophisticated framework for scientific computing. We do a lot of things, all our computation with Fil++. I will show you a few applications later, and containers are absolutely crucial to guarantee the availability of our software on various platforms and to be able to test in a consistent way on different testing and production runs. Regarding collaboration, for example, this is also extremely helpful because we don't know exactly the system where Fil++ will be used. And actually, we have quite a few colleagues who actually use directly Fil++ through the containers. Now you have excellent frameworks to help you work with containers in a very, very seamless way. For example, VS Code, Visual Studio Code, as part of the training, Visual Studio Code was one of the tool that we proposed that you installed. If some of you are interested, I can show at some point what to do in order to install the proper extension, but you have a very nice extension for Docker on VS Code, and then you can actually connect to a container very extremely easily. And that's what we are going to do actually when we are going to use CodeSpace. And then thanks to, not necessarily Docker as we are going to see, but thanks to Apptainer, we'll be able to actually deploy our framework on supercomputers. And as you will see, it enables us to do very rapid deployment and testing on supercomputers. Actually, on supercomputers now, we deploy only containers because for us, it's a huge gain of time. I mean, when I say it accelerates, I mean, it's just tremendous. Before containers, for us on supercomputers, it was just a pain to pour the code. Our software is a complex software stack with many softwares, many combinations. It was like hell, really like hell, in order to be able to compile our code on supercomputers. Containers have changed that totally for us for now, I don't know, 10 years at least. An important point is that the containers allow us also to archive our work and to preserve some older version and to enable reproducibility. This is crucial, and I will talk about it again later. So just to give you an idea about Fil++, let me scale down a little bit the image. Oops. Let me scale down a little bit the image so that it enters. It's too much. Yes. Okay. So just to give you an idea about the complexity of the software, at the very bottom, you have some of our dependencies. It's just a small set, a significant set, but a small set of our dependencies. And all the software also have dependencies. So when we pick them up, already we have a huge software stack at the very beginning to compile our code, right? And then we assemble some mathematical framework in order to solve PDs, to do physics simulation, mathematics, to solve academic to industrial problem, very large scale problem or small scale problem. So this is the blue part here. This is our mathematical kernel. This is Fil++. On top of it, we have some toolboxes in order to solve some generic PDEs from CFD, from solid mechanics, where different kind of physics, monophysics, multiphysics. Then, of course, we also need to have some reduced order modeling capabilities in order to reduce the computational costs if we want, for example, to do repeated evaluation for optimization, uncertainty quantification, inverse problem. This is a critical component now in scientific and high-performance computing. Of course, Python is also critical, and you want to have your Python bindings in order to provide scripting capabilities and enable, I don't know, people who are not familiar with, for example, C++ or command line. Here, you can work with notebooks and more, let's say, simple environments for developing. And on top of that, advanced methods to solve real-world application at the very top. So you see, we have a complex environment. We develop everything in C++. We have, of course, some Python, as I said, modern C++, C++ 17 and 20 currently. We'll move to 23 as soon as the whole stack is available in C++ 23. And this is a huge requirement for, let's say, for example, on an HPC environment, in the modules we use, if you know a little bit supercomputers, you usually have a module environment in order to load different modules, in order to be able to have access to the software. And usually that's where things go south because you have combinations that do not work out properly. So there have been actually solutions available now in the packaging world. We will talk about it tomorrow. For example, with solutions like SPAC and GoXHPC, because this is not only us. I mean, a lot of people have been stung by these difficulties. And so various solutions are now available in order to help with really complex software stack and have access to advanced software recent software on high-end supercomputers. To give you an idea, we have applications in the health area, rheology, microswimming, engineering buildings, high-field magnets up to 40 Teslas, deflectometry in ophthalmology. But I would like to present two important projects for us currently. I currently lead the Hexama project. Hexama is for methods and algorithms at exascale. Hexama is one of the projects of Lumpex. This is a French initiative for exascale computing. So we have quite a few projects, actually 5. And Hexama is one of them. This is the more applied mathematics one in order to have algorithm scale and be able to actually use the next exascale computers that will arrive in Europe this year, with the first one in Germany, in Jülich, the Jupiter machine, and next year in France with Alice Recoq. So these two computers will be highly hybrid, so you will need to be able to not only be able to deploy MPI application, but hybrid applications, so MPI plus GPU in order to be able to use properly the supercomputer. So this is critical that we are able to scale our algorithms, our methods for these machines, make sure that we have the proper framework. So it's about developing the algorithm for different kind of problems, for discretization, model inertia, solving linear algebra, inverse problem, optimization, uncertainty quantification. So this is critical for all this, but we need also to be able to deliver the software stack at exascale. This is a critical component. We don't want to have only a few software for this machine that are available, but a large brand of software that are available on these machines. So a big part of our work is to identify co-design, methodologic and algorithmic pattern for exascale. And another part is to actually use AI in order to help achieve exascale. And finally, we are developing mini apps and proxy apps in order to share our work. Mini apps to have demonstrators in order to go at scale, and proxy apps in order to be able to compare algorithms and within one application demonstrator. So this is how the project works. Here we have 6 work packages, and one is about development, CI/CD, benchmarking. So again, here you see that the CI/CD and testing benchmarking is critical. And of course, containers are critical. We have quite a lot of software. And without the containers, without CI/CD, without automated benchmarking, we cannot hope to succeed delivering the software in time for these capabilities. So this is a critical component to have containers, CI/CD, and benchmarking automated from the ground up, from the very beginning of the project, and not at the end. So this is one example. Another example is COE Hidalgo 2. So we are developing one of our applications in the urban building pilots. This is our contribution to Hidalgo 2. You can have some more information here if you want. On the left here, this is a reconstruction of New York with Central Park here. So you see huge amounts of buildings that have been reconstructed in an automated manner. And then we do building energy simulation. We do all kinds of statistics. This is deployed on, this must be deployed by the end of the projects on all EuroCC systems. We have already deployed that on many of them. And our stack is actually quite, um, our workflow, sorry, is actually quite complex. So let me zoom a little bit so that you can see here uh, how it is. So you go on the left here. So we have a few input tools. A critical one is Stereo GUI. From this GUI, we actually generate this kind of data. So here, that would be hundreds of thousands of buildings to millions of buildings that are generated. We have a big mesh, huge mesh, including vegetation, right? And from these GUIs, this is desktop or WASM application, then we actually deploy data sets on systems data management platforms, right? And we can trigger through the GUI orchestration system such that CI/CD system in order to deploy our application in an automated manner. Our framework here is complex. We need to generate a lot of different data. And if we have to do it by hand, of course, it will be cumbersome, not so interesting job, and we'll make mistakes. Here we have to automate everything in order to deploy the application up to the EuroCC or our own system or the cloud in an automated way. And then again, automatically the data is brought up back to large file storage systems. And then we do some post-processing, visualization. As part of the course, you will see another components of our work here, which is FieldPP benchmarking that will be done by Javier, and you will see how we actually deploy our application through this system in an automated way. And it uses everything we've presented earlier, containers, CI/CD. Those are critical components in order to do that in an automated way. If we don't do that, it's going to be very complicated, time-consuming, very slow process in order to be able to run our application. So we find that it's a huge gain in order to master these tools in order to actually run our development process and pilot application development. So going back to Field++. So Field++ is actually a core component of Stereo urban building, a core component also of Exama, and of course of this application here. So just to give you an idea about what we do with containers and workflows, this is a diagram of our CI/CD workflow. We'll go into the details of CI/CD later today and with the hands-on session, but still I would like to present you what we have set up now for many years. Of course, it evolves all the time. It needs to be maintained. We are making new additions. We need to move also with new systems available. So we start with events. So we have an event. So for example, we have a new development. We have a new pull requests on GitHub. On GitLab, that would be a merge request. Our platform is really GitHub. We do open source software. So we prefer to use GitHub for that reason, because most of the software, the vast majority of the software we use is actually on GitHub. So we start with a pull request event, and then in order to do a merge, we need to make sure that the merge will succeed. And that we won't have any regression. And then we actually build CI, continuous integration. So we have various environments at our disposal, and that we run. So we pull some images, some container images of the systems. We don't have all these machines at our disposal. We have some 2404 from Ubuntu, 2204 from Ubuntu, but no Debian 12, no Ubuntu 2004, no spec machines or whatever. So we pull those images and then we trigger build. We trigger about, well, we have about 1,000 tests in sequential and parallel that are being run whenever there is a pull request. And then when everything is fine, the Docker images are uploaded to the GitHub container registry. We will do that. We will work with this registry. And then if everything works, then we generate an Apptainer image because we need Apptainer for HPC systems. And then both Docker and Apptainer can be used by our projects or by colleagues or by other people. This is open. Finally, and I will finish with that, we are a small team, right? We are a small team and we do a lot of things. And if we don't automate things, we absolutely cannot handle all this application we are working on. It's not possible. We would get stuck with bugs, with regressions, if we don't, with time-consuming tasks that needs to be automated. So this is critical to be able to do that. Of course, it requires time as well. And then there is, so as I said before, we do a lot of testing, right? Whenever we have a pull request. But for the parallel computing part, we launch only small jobs. So if I'm correct, basically we have about half of the tests that are run in parallel, so about 500 tests that are run on six cores. So small parallel checks, but we don't have benchmarking checks at larger scale. And so we've set up some workflows as well, using CI/CD, using the reframe, and that will be presented by Javier later, tomorrow. And then we trigger whenever we have an Apptainer image. So basically, if this stage here is successful, we trigger a continuous benchmarking workflow where we use reframe and Slurm in order to deploy tests on various systems here. We retrieve reports and then we have these reports and we produce a dashboard website. So this is now a little bit old because now we have FIPP benchmarking. So you will see an even more modern way of doing this in the way that we have a nice framework in order to actually access a lot of systems in an automate way and generate very nice reports automatically. So you'll see that tomorrow and also a little bit on Wednesday. So let's start. So this is for the motivation for us, containers, CI/CD, and CB, and benchmarking, continuous benchmarking are critical components for our operations. I mean, we cannot work without this kind of settings, and this needs to be done. So just if there are any questions, don't hesitate to interrupt me and ask, because I'm looking at my screen, but I don't see if there are any questions. Yeah. Okay, so now that you know that we are very keen on these technologies, let's go back a little bit and start at the beginning. And introduce containers. So basically, containers, it's kind of CH root on steroids. In fact, containers have been around for a lot of time. It has been used, for example, on Linux for many, many years in order to be able to build new distributions. this is a very standard way of developing new and testing new distributions. So actually, we use it in order to do Debian and Ubuntu packaging on our systems. So containers are lightweight systems, but without any operating system kernel. So it doesn't run any operating system kernel. It's just the software that is available. So huge difference will be the startup time, for example. But the processes are isolated. The user level access is isolated, well, with some exception at some point. And maybe the most used tool is Docker. Hopefully, I'm up to my knowledge, this is the most common tool. You find it in many environments. This is the core technologies of many systems. For the cloud, for example, for the cloud, you have Kubernetes. Kubernetes is not attached to Docker. Well, for a time, it was most only Docker. Now it accepts other kinds of container technologies, but Docker remains the main containerization tool. It's a widely available, hugely used in industry, and you have a very important registry, which is called Docker Hub, where you will find a lot of software that have been already packaged for you. We won't use Docker Hub. In our case, we'll use it a little bit to get the Ubuntu images, but then we will use the GitHub container registry. So little bit of difference here with little comparison with the virtualization system. So a virtualization system usually embed actually an OS. So you have through hypervisor system where you have two types of hypervisors, and depending on the system, it's a different level of inside the system. Whereas you don't have any regarding containers. So the startup time actually, in order to start a container or a virtual machine is quite different. You don't need to start a kernel or whatsoever for a container, which is not true for virtual machines. And so also you have a very thin layer, or no layers actually. You have, for example, for Docker, you have a daemon running in order to talk to whenever you do a Docker command. But you don't have any abstraction of the system, whereas you do have through the hypervisors on the virtual machines, and that has a big impact on the performance. So for example, for us on HPC system, what we have seen is that there is, we did benchmarking on a few EuroHPC system, and we have seen little difference in performance between containers and without containers in terms of performance. So we don't see any major impact from this point of view. So this is quite excellent from this perspective and critical actually for HPC application. So you don't have this abstraction layer for containers here on the right, and this helps a lot with respect to the performance. This is a critical point. So now I already said a few things regarding the importance of containers for HPC. I would say it again. We have complex dependencies, complex software system. My experience as the leader of the Exama project, the Exascale French initiative, in the Exascale French initiative, we have a lot of software. Some software are relatively small. They are library components, quite small. But then you have others, a bit like Fil++, some of them, which are absolutely huge. So they have all complex dependencies. One aspect, and I already mentioned some messages. So one of the aspects is the so-called dependency L. I will get back to it at some point to explain what happens. So we have a lot of software. We have different machines. We need to handle all this combination. This is there are some. Module conflicts was something that where we spent countless hours on this, trying to find. Sometimes we even have to recompile compilers on systems. Actually, sometimes, quite a few times. So this is usually not good if you have to do that because you have to recompile basically the entire software stack. Similar to it is the fact that I know that there are a few people from Carolina here, but you have a centralized system, for the software, and you cannot. It's very hard. There are a lot of software available on Carolina. This is a very nice work that has been done. You can find on other EuroCC system a lot of software as well. But then the different combination may be very complicated, and some of the software may actually not be available. And so, if you have some custom and cutting edge software, that may be really complicated to get that. So, at some point, your fancy software may not have all the requirements available readily on the system. And then a very important aspect, especially for research. So reproducibility is critical, right? Be able to reproduce results, compare results, even after sometimes re-download the container is absolute, and being able to rerun on a supercomputer and check the results are still the same, or how we got the results for a paper, for a report. This is now absolutely critical. We spend countless hours on developing, on benchmarking. Reproducibility must be built in. And here, this is something very, very important now for us. So containers help with all this. One aspect is that now HPC application require, for example, for us, we require MPI workloads. We are working also on GPU. So having some of the hotspots in our computational frameworks to be replaced by offloading some of the work to GPUs. And so we have some specific constraints on HPC systems, right? For example, synchronization, being able to scale to huge amount of nodes, and we need to make sure that the software stack is actually optimized, especially, for example, the MPI suite rely on the proper driver. For example, for OpenMPI or MPitch, you need your network backend to be the optimal one to ensure that you will be using properly the networking infrastructure, the backbone of your supercomputer. And so the containers must be really fine-tuned in order to be able to use these systems. So this is a part where For example, Apptainer will play a critical role because it has been designed actually exactly for this. So if you have a few takeaways, leverage containerization to encapsulate all necessary dependencies and configuration. For complex software, this is critical. It's very difficult to do without. Very time consuming. You need an army of developers to do that, or excellent people to do that. But even so, it is very much time consuming. It allows you to create a single reproducible environment. So that is also a very nice property that you want to have. It simplifies the deployment process. We will see how. And you have consistency across different technologies. So, for example, you would see that the images, containers that we will build, the images that we will build and the containers that we will deploy will be used on, small machines with only a few cores up to an HPC systems. So to give you an idea, I need to reduce the page a little bit, otherwise you won't be able to see it. So to give you an idea about what I call the HPC-L. So here you have on the top, you have the machines where you want to deploy. You want to deploy on different HPC software components. You have laptops, tier 2, HPC center, tier 1 HPC center, tier 0 supercomputers. So you have many different systems, many different, I could put also the cloud, of course, here. And then you have the the code that you need to deploy, either the codes or some workflows, some libraries, some compiler and toolchain. You have a lot of combination, and this is really complicated to handle for a team of researcher, team of engineer that needs to deploy their tool on many different platforms. So containers will help you with this. So as you understand, well, for many years now, we have the HPC environment modules. We will use them, of course. They are very helpful, but in a way they are broken. One of a few reasons you don't have isolation. You don't have isolation, and this is something. When you compile your code, you have a lot of dependencies, and when you load the modules, you have some weird stuff happening that may happen in complex cases. So my last experience using only modules before the containers, it was on a French machine at TGCC. We were selected for a challenge before the machine was open to everyone. And I got stuck, but also the engineer team of the machine got stuck with their modules about what I was asking here. So a very complex bug that could not be solved right away, and we couldn't do anything. We had to stop the challenge on our side because of lack of isolation in the modules. So there were some very, very difficult combination that we could not see or debug easily. Then if you go from one machine to another, you won't have the same names for the modules, so very hard to have a consistent environment. May not be easy to ensure reproducibility for reasons also stated above. Again, the dependencies are critical here. So modules, basically, they offer an environment for sure very powerful, but unfortunately, for modern complex software stacks, that may be not the right solution. We'll discuss that with technologies also like packaging, like SPAC or GUI-HPC, which have been developed to actually solve also these kind of problems. So we'll discuss that tomorrow. So I'm repeating myself here, but these are the main points regarding the containers: isolation, consistency, reproducibility, portability, and reduce the administrator burden, the user and administrator burden. This is very clear. So now let's have a look at the container runtime. So now containers have been around for quite some time, and you have now access to a huge amount of software ecosystem around containers, workflows, integration in many environments already. Docker is really a core component in all this, but Apptainer is now used in many systems. So for example, at EuroCC, to our knowledge, Apptainer is on all EuroCC systems. So far, we have been able to use it on all the systems readily, and we deploy our application in a matter of minutes on the systems, while it could have been weeks without containers due to difficulties with compiling and the dependency. So let's have a look at the way Docker works. So we'll have a closer look at Docker. We'll start with Docker. That's what we do in our team. Why? Because Docker is a very convenient way to build images. With Docker, as you will see, you are able to stack up containers. And this is extremely powerful because it allows you to create and to stack your software, really a software stack, which is not the case for Apptainer. You won't be able to do that with Apptainer, for example. But then Apptainer will be able to, you'll be able to generate our Apptainer images directly from Docker, as we will see later. So Docker enables you to build in a very powerful way your image. This is quite simple. You'll need a file called a Docker file. We will do that in the end-on session. Typically, the Docker file is a file in your source code repository that you maintain. It's a text file, a few lines, and then perhaps sometimes more. And then you have a command build. This command build talks to the Docker daemon. There is a daemon running on your machine. And then it builds some container here, A, associated with the Docker file for A. And then you have a command called push. This Docker push will allow you to store the container on an image registry here that you will then be able to pull and run on another system. Again, Docker is running here, the daemon, and it takes care of the other suite of containers available on this system. So this is really the main commands that we use is build, push, pull, run. There are a few other commands. We will see that in the end-on session, but those four are really the main ones. Just for the vocabulary, we will use the Docker command line interface. So the command is called Docker. You will pass commands like build, run, push, pull. There are a few other ones. This command talks to the Docker daemon that can then handles the image management. So the image is actually the object that is stored on your disk at the form of, we'll see a set of layers with a manifest explaining what those layers are. So this is what's stored on the system, and a container is actually a live instance of an image. So basically, when we do Docker run, we start a container from an image, and which creates an isolated environment. The Docker file is a text-based file in order to build a container, an image, and the registry is a place where we will store, like Docker Hub, where we will store the images. I like this image from I took this image from the Docker presentation. This is an old one.
This one.
This is the container ID comes from the shipping container metaphor. And so what was the solution for the people in logistics in order to do the shipping of huge and very different goods? It was to create those containers that you see in ports, in train stations, everywhere, also on trucks. So those containers are, like very simple shape where you can put many different goods inside, and then this can be put on many different systems, trucks, train, boat, whatever. And basically, that's what Docker did. They actually created this nice environment for containers, for CH root. They really simplified the way it was possible to create containers. That's what they did. They really created a very simple environment for containers. It's a bit more cumbersome to use CH root systems. With Docker, it's really simple. And so what happens is that for developers, the developers are actually working inside the container. They focus on the code, the library, the configuration, and the operations. The people in charge, for example, of DevOps, they are working outside the container, or the sysadmin on the supercomputer system. They would handle the login, monitoring, remote access. They would provide different access to the container. So they have also this. So basically, you have a separation of concern here that is critical to solve all the issues I already mentioned many times. Inside the container, the developer is very happy. He has all his environment, all his tools, all his toys. And the operation guys takes care of the outside, making sure that everything is working properly. He can start, stop, copy, attach, migrate, do all kind of operation on this containers. But wait, Docker is not ideal for HPC. There are issues with Docker on HPC system. On our side, we use Docker. We give access to Docker to only a few people, because the thing is that when you have access, when you log into a Docker container, you basically can become sysadmin root. right? So you have elevated privileges, and of course on HPC centers, this cannot be allowed. So you won't find Docker for users on HPC systems. In our lab, we have Docker enabled for only a few trusted people that need to have access to Docker for development. But our students, our colleagues, researchers, they don't have access to Docker at all. They have access to Apptainer, right? But they can't build or run Docker images on our computing system. Also, if you want to run MPI application on advanced system, Docker won't work very nicely. You need a lot of setups of the networking system. It's not nicely integrated with Slurm or PBS or scheduling systems. So you need some extra work, and I don't think it's worth the trouble. And having access to multi-node workloads is not trivial as well. So usually when we work with Docker on our system, we remain on one node if we have to do on one node if we have to do that. It does not work. We haven't tried. Well, we tried, but we haven't pushed to have it work on several nodes. It's definitely doable, but I don't think it's worth the effort in this case because there are solutions, easy solutions that are actually targeted for this problem, and it's called Apptainer. So Apptainer used to be called Singularity, and it's now it has been developed in the American lab, and then there was this company created in order to support the development of Apptainer, called Scilab, if I'm correct. It was part of the development of the exascale computing program in the US, and now it's part of the High Performance Software Foundation, part of the Linux Foundation, HPSF, if you know about it. So there is a conference soon. If you are interested, you can have a look. There are several projects, and as you can see here, Apptainer is actually a solution that has been pushed to the Linux Foundation. So it's not it's not anymore under the umbrella of the American labs. It has been pushed to Linux Foundation. So now everybody from the entire world can contribute and do not depend on the decision in some labs in the US. So thanks to this very important decision, now a lot of tools that are available for HPC computing are now available under this new setting of the high performance software foundation. So Apptainer is really for HPC system. It has been built with this in mind. So the root access has been solved. So the user can operate and launch the container himself or herself without having a privilege escalation. So most important problem solved. It has been also configured to work with HPC schedulers. So for example, Slurm does the requests of the resources. So that many tasks on that many nodes, on that many GPUs for that much time. Well, actually, these informations needs to be available also inside the container. The container needs to be passed for MPI. So this is passed properly through the container. Another aspect is that you want to be able to bind your host MPI libraries or GPU drivers to the containers. So they have native MPI and GPU support. This is critical to get the proper performance. and they have a specific CIF format. We'll see a little bit, well, we'll use it. We won't dive into the format, but this is quite interesting because you have a single file instead of a set of layers, which is the case for Docker. There are advantages and disadvantages of the Docker file system as well for the CIF. CIF files enable signing. So this is also important for making sure that the container is safe and you can use in a safe way. So just some example here. Earlier, I talked about Docker build, Docker pull, Docker push, Docker run. We will see that in the hands-on session. And I need to finish soon, by the way. So here you see some of the commands that we'll be able to use in order to, with Apptainer. So with build, we can pull a Docker image and generate Apptainer image very easily. One line command. We'll be able to run our script, Python script, in a sequential way, no root required, or we will be able to run an API program also very easily. So you have here the different features for and differences of Docker and Apptainer. I think now this is clear, so I won't go into the details here. But you have basically a summary of what we discussed before. We use both in our team. So we build everything with Docker first because this is extremely convenient with Docker to build images in an incremental way. And this is part of our workflow cycle. And then once we have a certain Docker image level, so at a certain layer level, then we use Apptainer in order to produce specific Apptainer images to be deployed on HPC system. Container registries, we'll see, well, three. We'll use a little bit Docker Hub. But in fact, we'll use GitHub and GitLab registries. We will store the images on these systems. The session today, we will store on GitHub container registry the images that we will produce. But of course, you can have also your own on-premises solution, but you need to be prepared to deploy this kind of technology and to maintain them. So this is something that you need to ponder before doing that. Using a registry is extremely important because that's a way to actually handle reproducible environment. Because you will see that for Docker images or Apptainer images, you can tag the image and have, for example, version markers or a way to identify the images so that you can reproduce results with previous images, compare the results. So this is absolutely critical here, a critical feature for using registries. Of course, collaboration is another important point because this will be the way to actually collaborate with colleagues, even in your own team, but also with colleagues elsewhere in the world. You will see that actually GitHub provides a very nice environment as well as GitHub in order to manipulate the permissions for the images. You can really fine-tune the access to the images. Most of our images are public access, but we have also private access that we share with only a few people, some of our images. So this is extremely convenient. And lastly, but this is a way to be able to retrieve images for HPC system. Of course, if there is a policy restricting access to GHCRIO or some GitLab system, that will be problematic. But then there are bridges that can be built in order to move the data or the container data from one registry to another if this is needed. Okay, I will stop here. If there are any questions, you have, it's 10:38, so I'm 8 minutes late. We should have a break. If you have any questions, maybe I can take one or two. And otherwise, we have a small break before starting the course.
There is one question regarding Apptainer, but maybe this will be covered in the hands-on session. In the chat, there's one question.
Yeah, we can discuss that later, but indeed, regarding Apptainer, you can have a look on the Apptainer installation procedure. You may have to have, depending on the system, you may have to do a set UID in order to be able to run Apptainer. Apptainer has been developed in close collaboration also with the Linux kernel in order to push and pull features of the Linux kernel to enable containers in a safe way using Linux namespaces or in the user namespaces. You will see that we actually use an option for Apptainer called share NS, which makes sure that we will be able to use correctly the MPI application, but we'll discuss that later. Regarding the other questions, VS Code, okay. So yeah, you are not supposed to see a VS Code window. So I had to switch my network interface. I'm really sorry about that. And then it changed my setting here. So yeah. So let's have a break. Let's have a break, and we get back here in about at 11 o'clock, if there are no other questions. So the next step now is to actually understand a little bit how we are going to use the CI/CD. So I prepared a presentation like this morning. Let me go full screen now. So CI/CD fundamentals and GitHub Actions. So you will have the GitLab part. You will have the GitLab part with Samir, but a lot of what I'm going to talk about now is general and applies to both or all platform supporting CI/CD. Of course, with the hands-on session, we will actually work with GitHub, but there are, of course, a few differences between the two systems, but the principle remains. So let's go. So when we develop software, when we execute software, we face usually some kind of cycle. We have processes. So for a long time, until beginning of 2010, say, usually development had a series of manual processes. So you would develop your code, you would then have build, test, development. Usually all the steps were manual. And of course, since it's a human being who does all this operation, there are errors. So we may make mistakes when building, testing, deploying, and by using the wrong configuration, using the wrong software stack. So it's very easy. We may forget also some steps. And so beginning of 2010, I would say, there were we had the development of the continuous integration systems. Maybe before. I'm not an historian in this area, but there are a few dates where we had people presenting this kind of concept. Another aspect apart from the manual processes is that as a student, this is my own story here, but also as a teacher. As a student, I was kind of a geek. And so I've had so many times colleagues of mine who would say, yeah, I don't understand. It used to work, it doesn't work anymore. And you don't have more information than that, right? Or, yeah, it works on my machine, but whenever I go to another machine, it doesn't work anymore. So basically, you have this works on my machine syndrome here, and this is really difficult to handle. So you need to have some proper environment setups. This is critical if you want to ensure proper builds, testing. You need to have a clear path to actually build, test, deploy your software. This is especially true if you have complex dependencies, of course, but even for simple projects, and that's what we teach to our students here. They are from the beginning of master level. I would think that even before it should be taught, proper hygiene in terms of software development, testing, building, testing, deploying, and continuous integration. I believe that this is really critical. Again, about cycle, when we develop and test, and so if we need to do a lot of manual operation, that slows down how we work. That slows processes. And so, again, the human becomes a bottleneck, usually. And this is something that needs to be tackled. So we want to increase the time to delivery, or increase in the sense of decrease. Of course, we want to make it quicker. And also, we want to be able to scale. Our scale here is in large sense. It could be associate more people to the development. We want to associate more systems. We want to ensure quality, consistent quality across software. And usually this is difficult to ensure. And so here, CI/CD will be critical for all these aspects. This is something that is really that is there to tackle these aspects. Now, what does it mean for HPC in particular? We want for HPC application to have a consistent, reproducible environment. We already talked about it this morning. We want to have our specialized application libraries automatically built, available in the containers. Here we talk about Apptainer and being able to reproduce easily and avoid the works on my machine problem. So container will play an important role with CI/CD. They really work together. Then we want through CI/CD to automate tests. So that's why we have this C-test aspect. This is something that you really want at all times. Make sure that the software that you put in the container is tested. And so what we will do is that through the CI/CD pipeline, we will ensure that those steps are taken. So this needs to be checked. And of course, apart from correctness of the results, we want also performance, right? You will see that hopefully by the end of the Zen sessions with me, you will be able to make a small change, a change in your code, and commit the change, and automatically everything is rebuilt, including Docker, Apptainer, and then this is tested and deployed on the supercomputer. So this is incredible in the sense that in matter of minutes, seconds, minutes, in an automated way, everything is redone, and so you increase or you fasten, you make your development cycle much faster. And then you need to have access, or you need to be able to deploy on different systems, Carolina, Meluxina, Jupyter, on your own system at home. And so you need to make sure that across a number of systems, everything goes right. So you want to make sure that your workflows are easily deployed on all the systems. So CI/CD will help us with all this aspect, and I think this is critical. So in fact, CD hides two CDs: continuous delivery, one thing, and continuous deployment. Delivery and deployment is not exactly the same, in my opinion, but maybe opinions might differ. So continuous integration, this is how we work at Semosis. So usually we have the main branch in a Git repository that is protected. You cannot directly commit on there. And then we have branch developments, and once we are happy with a branch, we make a pull request. The pull request or the merge request on GitLab is reviewed. And at the same time is reviewed, actually the software is automatically rebuilt, retested, and we know that everything is all right with this software, at least with what we have in the test that we provided. And so continuous integration is critical to ensure that what you are going to add or remove or whatever operation you do on your software software. This is a critical step, and it's very transparent the way it is. Okay, do you hear me? Because I saw that my connection was unstable for a moment. Can you hear me? Okay. Sorry for the interruption because I saw the message. Maybe I stopped my camera. We do small pull requests, so small changes or larger changes, and we want to detect bugs as early as possible. Continuous delivery for me is really about packaging the software and being able to create those containers or those images and push them on container registry, or create Ubuntu Debian packages or whatever, or SPAC or GUIX, and then push them in the proper packaging system. Whereas deployment, it's more like, okay, now we have our software and we want to actually deploy the software so that it's actually executed and we get some result out of this deployment. So maybe it's a service that it's waiting for requests all the time. This is not the kind of thing that happens for us on HPC system. Usually we just launch through Slurms, for example, one job or several jobs. You would see with the benchmarking part that we launch, actually, we may launch a lot of jobs automatically. And then we get the results and we get some reports. And so deployment is about effective launch, submission of a job on a supercomputer, in our case, for the HPC context. So the benefits, all this. So if you have a huge software, this is critical to set this kind of thing, to accelerate your development, improve the code quality, reliability, faster time to market, and do work with incremental updates. So you have several choices for CI/CD. Since the end of 2010, so around 18, 19, GitHub Actions appeared. Before on GitHub, you would use Jenkins, Cycle CI, Traverse CI, Buildkite. There were several systems available on GitHub. It was quite open. You can still use them, no problem with that. It was great. But then GitHub proposed its own CI/CD system called GitHub Action. Before we were using Buildkite. Initially, we used Travis CI. Quite rapidly, Travis CI was not convenient because we couldn't use our own runners. I will talk about that a bit later. So we couldn't use our own infrastructure in order to launch our builds and tests. With Buildkite, we could, and it was an excellent system. And now we move completely to GitHub Action because we're very well integrated into GitHub. In GitLab, from the very beginning, CI/CD was incorporated, and so people have been used to have CI/CD in GitLab from earlier. It's a little bit different from the GitHub Actions, but the purpose is the same. And of course, you can use a different CI/CD system on GitLab as well as on GitHub. You could use Cycle CI, Traverse CI, or other type of pipeline system. Yeah. But then you don't have the advantages of the hosting entity GitHub or GitLab. For HPC system on GitHub or GitLab, you have the container registry system. So from your CI/CD, you can easily push and pull from the container registry. So for example, on GitHub, we use GHCR, the GitHub Container Registry System, and it's much more rapid than using, for example, Docker Hub, because it's much better connected to the infrastructure of GitHub. Also, depending on what you do, you may want to have your own on-premises with a self-hosted solution like Jenkins if you want to have some more security. Well, we do mostly open source, so it's not a big deal for us. But I must say that regarding self-hosted solution or self-hosted runner with GitHub or GitLab, you can actually have your deploy so-called runners or machines that will do the build, the testing, and that's what we are going to use. So we will use a little bit of the GitHub machines for the CI/CD, but we'll use also some machines that we have here in Strasbourg and also Carolina. We will see that later in the hands-on session. So regarding GitHub, so now a little bit about GitHub Action. What happens is that you need to create so-called YAML files. So YAML means yet another markup language. So it's a text-based file which has basically this kind of format. You could also have in JSON format, but it's a little bit more verbose, and I guess computer scientists prefer their YAML file because it's more concise. But then you have to be extra careful about indentation here. It's a bit like Python. You need to make sure that indentation is correct. You will see, however, that in VS Code, if you install the proper extension, namely GitHub Action extension, automatically the indentation will be verified, and you will see wiggles in the file if the indentation is not correct. So you will see errors, visual errors in the file, in the YAML file, if the indentation is not correct. I will try to show you that later and make mistakes. So how does it work exactly? It works the following way. So basically, it expects two main keywords, on and jobs. On is this is a trigger. On means, okay, we wait for some events to happen on the repository. For a given repository, you may have many YAML files if you like. This is really open bar on this, and a specific YAML file may wait for different events, so 1, 2, 3 different events, or one specific event, depending on what's being done on the workflow. So this is the event that the event block that is expected. So what are the events? Here you see two events. People doing, if you have a push, so someone did git push on the main branch. Here you see it's an array. So you could have a star here instead of main, saying that for all branches, we will trigger the workflow. Here we trigger the workflow only if we make a push on the main branch, or if we have a pull request on the main branch. So the following will be executed, the jobs section, that will be the next block that will be executed. It will be executed only if we have a push on the main branch or a pull request on the main branch. Otherwise, it won't be triggered. Remember that allowing workflows on any change of the repository may be energy consuming, depending on the size of your repository, because you will eventually do a lot of expensive operation, and so you need to consider to properly filter the events to make sure that you do what is really necessary. The sound is not good. No, it's better. Yeah. Okay, I hope. Let me know. Don't hesitate to raise your hand because I'm not. I have the chat on a different screen, and I'm not looking at it directly. So please raise your hand if you want to interrupt me or make sure that the video is lagging. So jobs. So once if we have this kind of events that occur, then we want to build. So build here is your choice. You choose the name that you want to put here. On and jobs are keywords. Push, pull request, branches, those are keywords of the YAML. Main here, this is your branch. Build, this is your choice. This is the name of the job. So build is a job. Then it will run on some machine. So on GitHub Action, you have three systems. You have Ubuntu, Mac OS, and Windows. And on Mac, you have actually both ARM and, well, both Intel and x86 and ARM systems. So you have both. However, if you are on free open source license on GitHub, of course, you don't have that many hours on the CI/CD system. I don't know exactly how many, but for a month, this is put back to zero. The counting hours are put back to zero every month. For us, we never reach the limit, but we use a lot our own runners, our own systems. I will come back to that later. You will see that here you can create your own runners and have your own system, your own machines run here. Then the steps. So what are the operations that you want to do? And so here you will have a bullet points, actions. So here, this is a so-called action. If you click here and I copy paste, I will see that in fact, action checkout, it's a repository of GitHub called checkout. And this is where the action lives. And the critical file is this one, action.yaml. This is the file that is read by the system here. There are, of course, a few other files inside, but this is the main entry point. This is a kind of main entry point for the action. And what you have inside is basically all the inputs that your action is taking. So the action here is checkout, and this is a very important one because it checks out your own repository. What it will do is that it will clone your repository and put you in the proper Git reference. So the proper branch, the proper Git reference to work with. And so you have also a README file. This is usually how it works, where you have the documentation of the action. By default, honestly, usually you don't have anything else to do, right? But sometimes it's necessary, depending on what you are doing, to check the options and look at what's available. It's extremely flexible. Feel free to read what's available. It's quite well documented. Another action, we use Node a lot, Node.js a lot for our documentation system. So for example, here, the website that you see here is created using AsciiDoc and Antora. Antora is built on top of Node.js and provides a very flexible framework to generate websites. You can select, you see, you have a nice language which allows to provide parameters. So here you have such an example. For actions checkout, you have also options, and that would be the same. You will have, the next line would be with, and then you will have, we will see that later, you will have the options, possible options for these actions. Now, another steps here, which has the name install dependencies. It will run the command npm. npm is a node package manager. It will run the command npm install or npm test here afterwards. So you can put as many steps as you wish. Or you could, yes?
Can I have a question?
Yes, sure.
So the field name is optional in description of the step?
Yeah, it can.
Okay.
So you are not, for example, for the checkout, yes. Usually you want to name it because you will see that in the GUI, in the graphical interface, you will see the name of the step, so it will be easier. We will see that later together, right? So it's better to name the step. I agree with you. There are some other, for example, you can have an ID for the steps, and this allows, for example, to actually communicate between the steps. So you can communicate information between the steps through a so-called ID. So but here this is a bit more advanced, so I'm not presenting it now. Okay, so yeah, just last comment on GitHub Action, and we'll see how to use it in the end section. We will start with simply running the test on GitHub. But the thing is, of course, you have steps which are your own commands. So for example, CMake -- preset default, CMake -- build preset default, and so on. So you will have these kind of steps. But then you really want also to have some actions which are already complex actions that you do not want to do by hand, like the checkout or cloning of your own GitHub repo. And in that case, you need to use actions. And you have a huge marketplace for actions. So for each GitHub action, so if you have action here, you can have a look at the marketplace. It's here. I can put it in there. Yeah. So you have a lot of ways to advertise your action. We have one or two ourselves. It's very easy to create one. It allows to simplify the way you and standardize and make it more consistent to compile or test your code or whatever. Yeah. So have a look. You can search for a lot of things. As you can see, there are a lot of tools also for AI, quite interesting. Okay, so now we will very rapidly actually mix, or maybe something I forgot to say, which is absolutely critical. You see here, this is the name of the action, right? So an action is a set of commands. We could do it with the steps here. We could absolutely do what this is doing through different steps. Unfortunately, it could be cumbersome and quite long to do. And so what people did is that they compressed all this operation within a so-called action. But then an action is also versioned. And so here at the end, you see the version of the action. So if I go back now to action checkout, let me show you again. So the version is basically the release of the action. And you see that you have to look at the tags here. So here you see that we have the v4 and all these tags. So if you select version v4, this is the latest version. And if you use v4, you have the latest, which is v4 2.2, right? So v4 is an alias for v4 2.2. This would be the latest. If you really want a specific version, which I don't, I think it's not a good idea to be specific for a version, but if there is a bug in an action, then maybe it's better to pull back to a version that works. But in general, it's quite well tested. So either V4 or specific. You should try to follow the latest version of the actions because they are updates of the underlying software stack. And sometimes older versions of actions are not compatible with newer version of the framework. Okay, yeah, thank you, Thomas, for the comment on the security reasons. Maybe you can tell more about that at some point. That's very interesting. Okay. So versions, you need to check the versions that you want to use, and I advise that you use something to stay up to date with respect to that. And usually they often bring also more optimized way of manipulating your CI/CD system. Okay, so our aim here is really to use a container inside the CI/CD system. So GitHub Action allows us also to work within containers. So you have the way to actually start on a machine a container and work inside the container using the steps. So just by doing this, adding this, you start a new image, which is node 14, and then you are in all these actions here, all these steps will be triggered inside the container. So this is quite interesting. We won't be using that today, but know that it's available. That way, you have a very consistent environment and you control everything in your environment, which is quite useful. If you work with Ubuntu latest, it comes with many software installed already. For example, if I check install software, this is relatively well documented. I just need to I thought that it would yeah, it's here. So for example, I can put that also in the chat. You have here for Ubuntu 24.04 all the software which is installed in Ubuntu latest, right? Personally, in our team, we often do not rely too much on this, and we usually work with our own images. But sometimes we use a GitHub-based image, and we are happy to find them with the software available. So they are quite complete. I mean, they try to offer a large brand of standard software on these images. So usually what you want is have your own environment readily available because it may take quite some time to install all the required software, and using a container is useful there. Okay, so that's it for GitHub Action. We now the next steps is and I think if maybe you have some questions regarding CI/CD. I don't want to go. I think it's better to do the training, the hands-on, so that we can go in more details, more specific details. But if you have any questions, feel free to ask them. We'll go. You have the basic principle here, or here at the beginning. It won't be more complicated than that. Of course, in order to go from compiling to building containers to deploying containers, it involves more jobs so it will get a bit more complicated, but not by much. Any questions before we get back maybe to the hands-on? So we'll have more time for the hands-on section. No questions? Let me check the timeline. I'm a bit too fast. Maybe we can make a break, or we can start the hands-on session if that's okay with you until 3 o'clock, and then we make a break at 3. So I changed a little bit the timeline. I'm sorry. So I was a bit, I didn't prepare maybe enough here, or I spoke too fast. So let's go to the training session so that we can go in further detail here. So now we are ready to start our Docker file. So the next step is the following one. First, we will create a Docker image with our MPI application. So this is the steps that will be taken here. Then we want to automate the building of the software. So in fact, this part should have been done this morning, but well, it was beginning, and there was this issue at the beginning. So I lost a little bit of time. So I would have started with that part. But since I was a bit faster, we can recover a little bit. So first, we learn about generating our Docker image for the MPI application, and then we'll see how to automate the process using CI/CD. First, the compilation and the testing, then generating the Docker image. Once compilation and everything is all right, we generate the Docker image, we generate the Apptainer image, and then we deploy using Apptainer. Let's go. Docker file. So, as mentioned this morning, the Docker file is a text file that will help us build our Docker image. So how is it? So I use callouts. So you have the explanations here. I won't show them here to you, but feel free to look at them. I will just go through the different lines here to explain what's going on. So the Docker file, text file. So this is here the text file that will be used to generate our first Docker image. So Docker image, you need to start from an image using the from keyword. There are some more advanced start point for a Docker file, but for our purposes, this is particularly fine. This is absolutely fine. And here we would like to start from an Ubuntu 24.04 distribution. So this is the name of the image. We want Ubuntu. I showed you this morning the Docker up page. And then here, this is a version or the tag of the image 24.04. I could have written here noble or latest or sorry, I'm not in the, yeah. Sorry, I have to change my I was not in the no. Where did I put? Sorry, I lost a window. Docker file. No, that's not the correct one. Ah, it's here. Okay. So I wanted to, yeah. Okay. Alors, but first I will go through this file and then we'll see how to use it here. So this is the starting point. So we start with a basic Ubuntu image 2404. Then we will have like from, so from, run, copy, work dir, env. Those are keywords for the Docker file. They are uppercase. You see they are specially colorized because this is a part of the language for Docker files. So you see that each command that you have here will generate a specific layer. I will show that later, what it means that it's a layer. So basically, we have a first layer, which is the Ubuntu 24.04. Maybe it comes with some layers also, but a priori, no. What you put here may have some. Then the next layer will be to install using apt-get some software. Here we don't have any cache of what's available on the system. So the first thing that you need to do is to actually update the apt cache and update the database. Then here you want to work in non-interactive mode, so you don't want to have a graphical interface triggered. So you need to say to Debian package that we work in non-interactive environment. Then we want to install some software. The -y states that we want to answer yes to all questions, and we don't want to install recommends. And then these are the packages that are actually necessary to compile the software that is in our repository. Alors, why do we do this here? Because this, when you build a Docker image, if you don't use this, if you don't use this, maybe you will install in your Docker image a lot of software that you don't require. And that may not be a good idea because it will increase the size of your Docker image. You want to keep your Docker image lean, not too heavy. So this is good practice to actually use this option here. Then we install the software here. We want Git, we want CMake, G++, Ninja tool to build the software, OpenMPI, Python. This will be useful for my colleague Javier on Phil Pepe benchmarking. Then we'll use these libraries. And at the end, you see that we do a apt clean. So we remove all the files generated by the apt install, and we remove some files here. This is really necessary in general to do that, to avoid that your Docker image is too big. Otherwise, it will increase in size. And also, that's one of the reasons we don't want to put one run per line. Well, it's a question of design. Here, I could have had one run command for each line. For each command? Why didn't I do that? Because as soon as I do apt-get update, it creates some files on the system, a kind of cache, and the layer is stored. At the next command, here it installs some files. So I will have yet another layer, some files are stored. And then I do the clean and remove the files. In fact, these commands here won't be useful at all because all the cache and information about the package that could have been removed, in fact, exist already in the previous layers. So that's why we usually condense all these comments in one line to avoid duplication of unwanted files in the layers. So this is also a good practice. Now, depending on your objective, you may want to split nevertheless those comments to use the layer system of Docker. That may be useful depending on what you want to do and your build processes. Then what we will do is that we will copy the context, our repo. So we copy our repository. So you will see we will put the Docker file here. And when we do Docker build, we will actually copy the whole repository inside the container, and we will put it in a directory called workspaces MPI hello world. Then we state here that the current directory will be that one. So it's like we did a CD. We change the directory to this one. So this is now the current directory. So we are at the top level of our GitHub repository. I will skip these lines for now because this is a little bit specific and not that critical. Well, a little bit, but it avoids having warnings or error. Well. And then here, a bit like here we actually configure, build, test, install, and remove the build. So this is our workflow, right? Compilation workflow for our software. So this is it. That's it. This is a file. So let's copy it. I can copy it here, click, and then with the right button, I create a new file here, and Docker file. And I copy paste the content of the file. Now, a little problem is I have this parentheses here everywhere. So I'm going to select them and simply remove them. No, maybe that was not a good idea. So let me copy paste the Docker file here. I put it in the Zoom chat. I removed for you the callouts that are here with the explanations. So let's go. We have these files. So what do we do? Docker build, Docker command, Docker build. And what we need to pass is the name of the image. So the name of the image will be C3B, for example. I can say, for example, V1. This will be the version, and then dot. So T is for tag. So that would be the name and version of the image. And dot is the current directory. So we want to use the context to build the image would be the current directory. So I simply do this. Alors, there are some, I didn't see that I didn't clean up properly. Let me put back the version. Yeah, sorry about that. So the error here was because I didn't clean the parentheses correctly from. So now should be good. Let's look at what is going on here. Docker build. So what it does is that it looks at the context. It downloads Ubuntu 24.04. It found it. No need for download. So here you see you have the first, it detected 5 steps. So it did the first steps. So the from. Now it's at the second step. It does this part. So it downloaded the packages. Now it configured the packages. So what you see is what's going on inside the tree. So now it does step 3, and of course there is yes. That's actually that's excellent because it shows it shows an important thing. So you see, we failed at step 5. So step 5 failed here. So why did it fail? Let's have a look. It states that there is a CMake error. The current CMake cache directory inside the container is seems incoherent with the one in the workspace. So there is some mismatch here. So why is that? It's because this morning we actually built the software, and there is this build directory here that was generated by our work this morning. So in order to fix this, simply remove the build directory, because now we will build actually inside the container. And what we did earlier was actually to copy, here, line 9, we copied the entire repository inside the container. So we copied also the build directory. So now have a close look about the build process. When I restart it, you will see the layer system at work. Here, step up to step 4, it was immediate. Why is that? Because all the layers have been considered unchanged by Docker. We didn't change anything in the file. So everything is already available. All the layers are already available. What has changed only is layer 5, because it failed before. So it restarted layer 5. And as you can see here, everything is all right. So now it's all good. And you see, it did the CMake preset, CMake build, C-test, everything is working. Everything worked, no errors. It should be operational. And in the end, I have this image. So let's have a look. Docker run C3B V1. Alors, we are going to connect on it. So I add, let me copy paste this command to your to the Zoom chat. So let's do it. So you see, I'm inside the Docker image. Again, here you see that this is the host name. If I do a Docker PS, I would see that this image, this container has been created. This is a special instance of this image. And I'm root. ID, I'm root. So the application is called my app. I don't remember, did I do? Yeah. Yes. Okay. So I forgot to change one file. This morning we had to change some files, and you see the install command that I put here, which is also the install command here, should have installed our application. But I forgot to tell you and to do a change to the CMake list inside CMake here. So I will give you in a moment the content of the change. I'm really sorry, I forgot that step. Oh, I need this guy. No, I need. Okay. So let me put the proper version. I put it in the Zoom. So I replace the content here. If you click on source control, you see the change I've made. So I forgot here, well, I forgot. I have a working version here, but the GitHub Classroom actually picked the earlier version, and I made changes after I generated the classroom. So really sorry about that again. And this is required to install our target, right? So we have two changes. We have this Docker file here. We have this small change in the CMake list, which is in my app. So you have to change in my app the CMake list and add those 3 lines here. Basically, it tells you to install my app into the bin subdirectory of the root installation directory. So we need actually to rebuild the image because now we change the CMake list, so we need to redo it. I'm going to remove build again, and oops, and I'm going to rebuild the image. So Docker file, CMake list. I'm going to rebuild the image. And you see again, we didn't change anything from the first steps. So it goes very fast. Everything has been done. We don't need to make any change. It's only the last steps that will be required to do. So when you have a very complex, very heavy Docker file with very heavy steps and not so heavy steps, that is very useful to debug and make quick changes if you have to make a change at a specific layer in order to correct a bug or fix something or whatever. So now we can run again, and now we have my app. My app. So we need oversubscribe because we don't have enough processes. And so I can run with this. It works. I am inside my Docker image. I can run my application. Of course, in code space, we have only 2 cores. and we need to use this oversubscribe option because we are in core space. You can actually put, say, 10 here if you like, but you have only access to 2 cores. Now, let me go back to the options I left out and I didn't explain here. There's 2 options. So as you can see here, we are root, right? And MPI doesn't like that you are being root. And so it complains that you are running MPI. And so basically, if you don't do this, if you don't use S options, you will see some messages, error messages saying that if you really want to run as root, you need to actually use these two environment variables. You are not obliged to do that. If you create a new user inside the Docker image is really doable. Here I didn't do it, but you can create, it's a Unix operating system, so you can create a new user and then change the user inside the Docker image. I'm not documenting it here, but you can find many references online, and then switch to that user instead of root. And in that case, you don't need the line 14 and 15 in order to run your MPI application, right? But you will see that for Apptainer, that won't be a problem because we are never working as root, and so MPI will not, MPI run or whatever won't complain about this. Any questions so far? Any questions? No? Can I move forward? So what I suggest is that we keep those files around. We do not commit them yet. And we will get back to, we will commit them once we have the CI/CD ready. So now, some questions that you might ask yourself. Can we do the image differently? So here, a little bit of best practices here. Again, be careful about how you build your images. You want to keep only the necessary images. So remember these particular options here to avoid installing recommendation instead of exactly what you want. Instead of just installing exactly what you want. You see, having CMake presets allows you to have a very nice and concise build process. I strongly advise that you learn about that if you are a CMake user. Honestly, this is a huge progress when you have a complex software. This is a time saver, a tremendous time saver. It helps everyone, your user, yourself, your CI/CD. This is extremely convenient. This is really CI/CD friendly. You want to keep your command line and your CI/CD clean. And don't forget to clean here once you install app packages. This is true also for RPM, for you, for any packaging system. You need to clean the environment right after you install in the same layer. Otherwise, you will keep files around. Idem here. So what could we have been doing a little bit differently? Actually, the cleaning stuff we could get rid of this by using multi-stage builds. So we can reduce. So if I quit here and I do Docker images, where is my Docker image? Let me, yeah. I don't know if you see my screen. C3B is here. C3B is here. As you can see, the size of C3B is 1 gigabyte, right? The tag is V1. The image is called C3B, right? Let me have it on one line. Yeah. So the image is C3B. This is V1 6 minutes ago, 1 gigabyte. So is there a way to make it leaner, smaller? Yes, there is. The way to do it is to use multi-stage builds. The version pinning, so with tags and stuff, would be is very useful. So do not rely on latest. Latest can be convenient sometimes in order to point to some specific version, but latest may not mean the latest version. It may mean the latest stable version, for example, which is not the same as the latest version. For Ubuntu, there are new distributions, but not LTS, not long-time support. So latest may have different meaning depending on the software. So I would suggest to not rely on latest, but have your own branding or own tag systems for your software. So proper version pinning is critical in order to ensure reproducibility. And then again, the layer system can be used to accelerate and organize and accelerate the construction of a Docker image. You have seen here that we made some mistakes. Well, mistakes. We had this build directory inside our repository. And when we copied here, we copied also the build directory. And then when we reach this stage, there were some inconsistency with the CMake cache that CMake found. And so it stopped the process with an error. We had to remove build, but then only this step was redone. All the other steps were already done. So it's a huge time gain. So let's have a look at multi-stage. So what is multi-stage? But basically, it's a two-stage system where we'll have a build stage and a runtime stage. So the build stage will be basically what we have been doing until now. But then we'll have a new stage called the runtime stage where we will actually copy back what we have been doing, but only the relevant and runtime aspect. That will change tremendously the size of the Docker image. So the steps in order to build and run are exactly the same, but you see now the image is slightly longer. So let me put it in Slack. This is already the, no, it's too long here. Can I put it in Slack? Is it okay to put it in Slack?
Yes.
Let me put it in Slack because the Zoom does not allow. Yeah. I put it in Slack, but there are only 12 people here. So how do I can put it maybe in so I put it into two parts in Zoom. So this is the first. Oh, it's already too long. No, it's too long. Sorry about that. Yes, thank you very much, Andrzej. So Andrzej gave you the link to Slack so that you have access to. I didn't know that there were limitations in the Zoom chat. Sorry about that. Otherwise, you can copy paste, but then you have to remove these callouts here. I need to find a way that they do not appear like this. You can just copy paste this, but then you need to trim and remove those lines. Actually, they are in the comments, so that should be fine. Let me try it. So what we will do now, I will create another file, and let's call it Docker file multi-stage. So now I have two Docker files, and I copy this. So if I'm correct, it's in front of each. Yeah. So that's good. Actually, you can copy paste. So the first part here is the same as before, except for that part as builder. So this is a new part of the language. So from comes in different flavor. And here you can use here as builder. So this will be the build stage as soon as you use this after from and the image. So this will be the part where you build your software. And then the second stage. So we start with 2404, but this time this will be the runtime. So what we will actually execute. And here, this is slightly different. We still have a few things which seems to be similar, but here, look at what has been installed. Here, I have only dynamic libraries, OpenMPI tools, no development files. Whereas here, as you can see, I have the compiler, I have Git, I have CMake. This is for developers. This is the environment for developers. Whereas here, I just want the image for the user here. So I removed all the extra stuff, and especially all the development environment. So I keep only the tools and the dynamic environment. Apart from that, same way, you use this, you clean, yeah. And then here you have the copy command, but with a special argument from builder that allows to copy what we have in USR local in the builder stage to the USR local of the runtime stage. So we installed actually our application in USR local. So let me check for you that it's actually the case. So if I run here and then I type my app, yeah, my app is in USR local bin. So I just copied the content of USR local from the builder stage to the runtime stage. You can copy whatever you want on using, you can have as many copy commands as you wish in order to build your runtime environment. Again, the work directory will be workspaces, MPI world, MPI hello world, and then we will need those guys here to ensure that MPI does not complain that we are root. So in order to build the image, it's exactly as before. No change. But then, oops. But then here I want to keep both versions. So let's call it V1 multi-stage. So I change here, I create a new image. And you see everything that we have done is mostly already, it's extremely fast because all the initial part was already done. All the initial part in the builder was already done. This is the same as before, except for this. So it was extremely fast and already cached. Then what it does, it did only the very end because probably there are some slight changes, but it was quite fast. So now we are, sorry, I forgot something. I need to, up, I put that into the Zoom chat. So I forgot to pass the proper Docker file, right? So basically, I rebuilt the initial Docker. So now with -f, I can actually pass the Docker file I really want to use. But what I said earlier is exactly what, so you see, we are already in the runtime stage. So everything, what is it doing? Oh no, I would have thought. Yeah, it's installing Fortran. So, okay. So it does actually. I thought that it would recognize that some of the layers are already available, but maybe the fact that we use as builder here, it's restart almost from scratch. So now you see we did the builder stages and it's almost done with the builder stage 5.5. It finished it and now it's back in the runtime stage. In the runtime stage, it already did that part. It's totally independent from the builder stage. But as soon as you have this, it has to wait for the builder. So here for these stages, it was independent of the previous one, so it already did it. So it really uses parallel or multitasking here in order to have a quick build process. And once it finished the builder stage, then it does, in the runtime, it copies the files and sets the environment. So let's get ready for a big surprise regarding the size of the images. Our initial image, C3B here, V1, 1 gig. Our C3B V1 multistage, half. It's quite significant. And here, this is a very small software, right, that we built. So imagine for a more complex software, you will have a much bigger image. So you see, just with a simple software, we already gain 500 megs, which is quite good. So whenever you will pull this image, it will be much faster with this. Okay. And of course, we can execute, we can run the image multi-stage, Docker run multi-stage, and my app, again, we need to run my NP8 over subscribe my app. All good. I don't have anything locally. You see the software that I had before. If I load the V1 instead of V1 multi-stage. If I load the V1, then I will have here the repository with the software, all the environment. I would have a lot more software inside the image. Here, this is really only the runtime environment I have access to. And so if I look at USR local bin, my app is here and I have only that. Any questions so far? All good?
I might have one question if I can.
Yeah, of course.
Do you know,
go ahead.
are those...
You know that you always can. You just
Yeah.
raise your hand, and I'm really happy to have questions.
Just maybe some off-topic question, but are those images somehow compressed?
This is a good question. I believe that there are some sort of compression here, but I'm unsure. So this is an exercise. You can have a look. Definitely, you can ask. Let's ask, for example, let's chat. A are the images compressed somehow. Yeah. So you see that they use some compression system, but as you can see, it's quite fast. Yeah.
Okay, thank you.
Yeah, compression is critical in many of these environments. I never really thought about that, so thank you for the questions. Okay, so next steps. So we did this. So now, before the break, so we have 5 minutes now to actually push the image on our container registry. So the steps are there. Let me push. Yeah. So this morning you had to do this, right? And so if I try to do push C3B V1, for example, what it says, so it's as simple as that. What it says is that, yeah, okay, I try to push on Docker.io library C3B, and then it says, oh, access token has insufficient scope. Doesn't work. So what happens here? What happens is that what we use for the name of the image is not actually implicitly says that we are going to use Docker Hub. And in fact, what we created is a token to use gscr.io, which is a GitHub container registry. So we need to actually rename our images. So renaming our images is simply, we just add gscr.io here, and then the organization. I need to increase the size of the image. So here, let's say that it will be faster to use C3B multi-stage. So here you will put your login here. So here, for example, I will put freedom. If I do that, no, sorry, it's not. It's not 2 dots, it's slash. Yeah. So if you do that, you see renaming an image, it's immediate. All the naming of the image is done at the very end of the Docker build. So renaming is instantaneous. So what we did here, we said that the image should be stored on gscr.io. Here, Prud'homme, alors you have to put your own login because you don't have access to my own package space. And then you keep that guy or whatever name you gave or version you gave to your Docker image. So now let's push again. So now I need to actually push exactly that guy. So let me put this on. Let me put this in the Zoom. And then, of course, you will adapt again with respect to your own environment. So let's do it. Marvelous. It works. It pushes. You see? It pushes to some place.
Why there are 4 progress bars?
Sorry?
Why there are 4 progress bars, but not only the one? There's 4 items pushed?
Yes, yeah, 4 layers. One layer. You see my screen?
Yes, I see your screen.
This layer is pushed. The from as runtime. This layer is pushed. This is the second layer. This layer is pushed. And then this layer is pushed. 1, 2, 3, 4. The env is not a layer, but you have 4 layers exactly that are pushed.
Okay, so each layer is pushed. Okay, thanks.
So that's why, and they are pushed actually in parallel, as you can see. And this is an optimization. So now I need to look where are my images. But simply you go on GitHub here, and you click on your little icon. You look at your profile. And when you click here on your photo, you click on profile, your profile, and you see here packages. And C3B is here. By default, it's private. So the package is here. Let's have a look. So if I click on C3B, I have, you see the label here. It's private. I have this label. I have latest. This is the manifest. I see it again here. I have all kind of information. Those are the layers. So regarding the person who asked a question about compression, you see that it uses gzip for the different layers. So you see this is a layer where we actually copied some stuff. Here also. So here, this is the apt part. And here, this is the my app part. The rest is insignificant, very small. You have some package setting. So what you can do here is that on this page, so again, you click here on your profile, packages, and then it should be here, right? Only you can access it, it's private. So what you can do is you can connect to a repository. And so, for example, you look for there. Maybe I need to COE. Maybe I cannot connect it here, but we'll see later with the CI/CD how that works. Actually, you could try if you join the team, if you join COE Hidalgo 2, I sent you all an invitation I sent you all an invitation to COE Hidalgo 2. You could try to actually upload. I'm not sure if that will work. We will see. So you could try to actually change the name and replace your own login with COE Hidalgo 2. Right? You could try to do that. We'll see if the permissions, I'm not quite sure that that will work, but in the CI/CD, that won't be a problem. It would work. So let's do this. So I rebuilt the image with this. Actually, maybe here, what you do is that you put your login at the end, because if we all name the image with the same name, then of course, some images, there will be some conflict, right? Because we will have the same names, the same images that will be overwritten on the packaging system. So you could try to do this. You put your login, you replace your login by your own login. So let me try to do this. Put on here. Then, okay, I rebuild the image, and now I can do a push. If I do a push, push, and push, and it worked. It's already there, quite fast. And let's have a look. So I am now on COE Hidalgo 2. I have the packages are here. Oops, I don't want that guy. I want C3B. And you see that the image is here on COE Hidalgo 2. Now I can connect the repositories, and I can say this guy. But that might not be a good idea, because if I do that, it will be connected only to my repository. So in practice, of course, it's better for the course that you use your own organization, your login organization. But for the CI/CD, you will see that things should work out hopefully relatively okay. We will need to make sure that the name here contains your version, your own version. Otherwise, we will step on each other's toes. Or if we use COE Hidalgo 2. If you use your own logging organization, then you can skip here, Prud'homme, or you can skip your own login here, and you just use your login here, as I showed before. Does that make sense? It seems I'm the only one who did that, so maybe the other ones don't have the permissions to do it. Okay, so yeah, it's 3:05. I hope that you managed to build the image, to do the Docker build, the Docker push, and see how that works. So we should have stopped at 3, but we managed to finish the Docker and MPI part. So I propose that now we make a break. Get back now, 3:20. Okay, so let's recap a little bit. So what we did so far, we set up the environment in CodeSpace. We used Docker inside CodeSpace. We logged into Carolina in order to pull an image, a Docker image, and then run it inside Carolina. Then this afternoon, we saw how to build a Docker image of our repository, and to do it two ways, a single stage Docker file and a multi-stage Docker file. To do that, let me put here again in the Zoom chat and in the chat, yeah. I needed to change the CMake list of my app. This is critical for the next stage. Huh? Otherwise, we'll have this won't work properly. So you really need to edit the file CMake list, and you need to add this at the very end. So I put on the Zoom chat again the content of what I have in my CMake list, right? So you need to edit this guy here, right? So basically, those lines have been added. And this will be also necessary for the work here. We'll have this Docker file and this Docker file. So I can, maybe what we'll do is that we have seen that the single stage, let me rename the file here, single stage, right? So I renamed it, the one with single stage, I renamed it here. And the one which is multi-stage, it's the default one. So now the Docker file is this one. It's the one that is available here and that we can copy. Let me put the link to the page here. So this is a link to the web page you can use. You just copy and then you put it in the Docker file. So this is the Docker file we will use for the remaining of for the remaining of the day and also tomorrow. So this will be the default version. Why? Because we'll use push and pull, and since if it is much smaller than the other one, it will be much faster in terms of communication, network operation. So a question I didn't have earlier is that nobody asked, okay, but now we did Docker, but we have to use Apptainer, right? Regarding Apptainer, I don't remember if this morning I mentioned that, but you don't have access to Apptainer on CodeSpace. Why is that? In fact, you could install it. You could install Apptainer in the Docker file here. You could add steps from the Docker, from the Apptainer website. The installation steps are available. You have Debian packages for Apptainer. You could install them. Unfortunately, Apptainer cannot work inside Docker. So you cannot use Apptainer inside Docker. So you need to do that on another system. So here we can check actually the image that we actually built and that we pushed. So first, let me, so that everybody can do it, let me make this image, so you see this is a C3B V1 multi-stage. I'm going to make this image public so that everyone can use the image I produced here. So I go to package setting. You could do that with your own as well. I mean, you have the permissions to do that, of course. So you go here in package settings, you click there. You go down and you can change the visibility and make it public. So here you need to type C3B, you click public C3B, and then you click there and the image will be available publicly. Anyone can actually download your image. That's it. And now visibility is public. So what does it mean? It means that if I put that in the Zoom chat, you can actually do it in CodeSpace. You can retrieve the image I produce in CodeSpace. In my case, the image is already there. So no need to download it. It's already available. So we'll stop that. I think this is the end of the training today. I hope that you got, I didn't see the question. No, okay. I hope that you managed to do a few things. I see that a few workflows have been launched, so that's good. And see you tomorrow for the last steps and finally deploy our jobs on using Slurm automatically on Carolina. And then benchmarking will be great. Hopefully you will enjoy it. Thank you. So, quick recap of the first day. So, we had an introduction on containerization. We saw that containers are great to deal with complex dependencies and to have a specific system for your own code in an HPC environment. We saw two technologies, Docker and Singularity Apptainer. Docker is very, very popular, but was designed for the cloud. It can be used in HPC context. Definitely, we can run MPI application inside a Docker environment. However, on a multi-node system, it's not adequate and may be cumbersome to set up. And it's very easy to create a Docker image. However, there are some things to know about how to properly design your Docker images. On HPC system, we saw also Apptainer, and Apptainer images can be easily created directly from Docker image. Docker is more suitable for image creation because it has a layering design which allows to pile up images, which is great if you have a complex software stack. Whereas Apptainer, you don't have this feature, so it's monolithic there. But it's fit really for HPC system. You can easily bind your libraries, your host libraries, for example, MPI, to the guest image. So containers are now really a fundamental technology in order for development cycle, to ensure reproducibility, to ensure compartmentalization or isolation, development or compilation. We had some hands-on session about this, and then we saw that Containers, well, we saw another technology, which is continuous integration and continuous development, continuous delivery and continuous deployment, sorry, using GitHub Action. Well, it was a generic presentation of CI/CD fundamentals, a little bit of GitHub Action. The principles remain the same for GitLab. There are other systems for CI/CDs. GitHub and GitLab offer their system integrated into their Git platforms. And this is also an important, let's say, tool set in your own development cycle. And containers and CI/CD play together very well. They are actually they can be used together to actually compile, test, and deploy your software in an automated way. So yesterday afternoon, we saw how to build our software using CI/CD, how to create a Docker image, and then how to generate an Apptainer image from it. We played on Carolina a little bit. So now we are ready to have a few advanced topics. Some of them we will implement them in the hands-on session this afternoon. Not all of them, we don't have the time, but I will discuss nevertheless a few options which we have implemented locally and which we may present in a future training session. So in the hands-on session, we will finish the job and we will see that we are able to automate completely the entire development cycle from building the software, testing it, building the image, generating the Docker image, generating the Apptainer image, and deploying on Carolina or another system. So we'll deploy on two systems in a totally automated way. So this is the objective for this morning. So this afternoon, you will have the reframe-hpc and initial benchmark setup presentation by Javier. Tomorrow morning, you will have the presentation about GitLab from Samir. And tomorrow afternoon, the second part of Javier's presentation on FieldPP benchmarking. And in that case, you will see how to deploy benchmarks, a huge amount of benchmark potentially on a EuroCC system in an automated way, and also a very nice reporting system. Okay, then it's 9:30, so we can start with today's topic. Let's go. No, that's not the good one, sorry. Oof. So we'll see various topics about CI/CD, well, still a little bit of containers, of course, using GitHub. First, I'll start with SPAC, the SPAC system. So our colleagues from the US, from the national labs, developed SPAC a few years back. Actually, maybe it's 10 years, more than 10 years now, in order to solve the software dependency L for HPC platform. So this is what I presented yesterday. I mean, how do you cope with such complex software stack? So SPAC is an open source software package management tool for HPC and scientific computing. And I would like to stress the end of the sentence. What I find nice about SPAC is that it was done by people having HPC and scientific computing in mind. And so quite often when I learned about SPAC, I mean, I was wondering about, hey, can I do this or can I do that? And most often the solution was the one that is most beneficial as a user. I mean, it's really convenient. And even though a few of these people are computer scientists, almost all of these people do HPC or scientific computing. And so they know what you are facing, right? So the options that they provide or the features that they provide, I find them very well thought, um, and basically what you would expect most of the time. I don't have any example of cases where it's not what you expect, quite the contrary. So it's really made for what we want. So it's quite nice from this point of view. So what is critical with SPAC is that you can install and manage multiple versions of a given software. So SPAC acknowledge the fact that depending on the stack that you are building, depending on the software stack that you are building, you may require different versions of a given software because of the dependencies that you are facing. So you need to be able to install and manage multiple versions. Then there is the software dependency hell. So in that case, you may require very intricate dependency trees. I will show, I have one graph later that shows the complexity. I did it also for the software that we develop. It's incredibly complex, and it's impossible to actually control the software stack at all. I mean, as a developer of your own software, it gets very complicated to understand all the ramifications of what you are developing. And so you have a very complex dependency tree, and you may need very specific compiler configuration, depending either on the software or on the platform. So this is also this is important. So SPAC now is available on some EuroHPC system. For developers, but also for production. I believe that I'm not expert in this area, so maybe the people from Carolina, if some of you are expert here, my understanding is that on a supercomputer, giving SPAC access, for example, to end users might be complicated because it creates SPAC is huge, and it would generate, when you install new packages, for example, with complex dependencies, then you may create a lot of new inodes on the file system, and so that may be not good for file system performances, for example. So my understanding is that there are some difficulties to provide direct SPAC usage to end user on supercomputers. What happens is that on a few systems, the sysadmin of the supercomputer provide modules based on SPAC. So SPAC provides a feature that allows to generate modules out of SPAC packages. So this is quite convenient, because basically you use the power of SPAC to generate the modules for you in an automated way. In our case here in Strasbourg, we have our own SPAC software stack. We develop it locally. We also have pushed a few things into SPAC, and we have to use it in in the Exascale French initiative as part of the solution for our software production. So a few motivation. Yesterday I talked a little bit about our experience in software complexity, looking at how things are going these days. Software complexity explodes literally. We have new software popping up using many libraries, in libraries eventually having themselves dependencies. And so that could be potentially hundreds or several hundreds of software dependency when you install a new software. That's the case, for example, for C++, by the way. Some years ago, the idea was to actually use a component-based development approach, and that was indeed a good solution. So now we see that this is done at the worldwide level, where software use bricks from this software, that software, those software, these libraries. So this is pretty amazing. However, connecting, integrating can be extremely difficult. You have, of course, the common build time error, so it fails to compile. So that's good because it fails fast, but then you need to fix it, right? And might not be that trivial. But the other problem is that when, the build went fine, so you can indeed assemble the system, but then you have holes in your system, and eventually you will get failures later, runtime failures, for example, but it was not detected initially, and that may be actually difficult to find about. So this graph here, let me zoom a little bit. I cannot zoom more. You can see eventually some names here in the little box. This was done with Dot from GraphViz. So the red boxes that you see here there are about 100 red boxes on the graphics. Those are the software that are installed by E4S. E4S is the platform, the software stack for ECP. And the blue box, you have about 600 of them, are the dependencies of the red boxes. So you see just E4S, the software, the Exascale software stack, American Exascale software stack, about 100 packages, 600 dependencies. So it's huge, right? So it's not possible for a human being to handle this complexity. Forget about it. So another thing in HPC software that we encounter is the fact, and that we do actually, for example, here in Strasbourg, I can talk about it at length, is that in practice, you mix usually open source and internal packages, sometimes proprietary. So this complicates build, that is, you may have different ways to integrate software. Here, CMake, we used CMake yesterday. CMake offers several mechanisms to include software, and depending on the context, you may use this or that feature, but still, it may be difficult to combine various ways of integrating software into a software stack. Another thing is that when you go to a supercomputer, there is no one-to-one relationship between the source code and binary with respect to performance. So you need to be able to adapt the software to get the performance. You don't have portability across system, across supercomputers. You cannot move binaries from one supercomputer to another. Usually that's difficult. Actually, GoX HPC, which is another system we'll talk a little bit later, enables this kind of thing, and maybe SPAC soon. When you are on a supercomputer, dreaming for a single tool chain is usually very difficult. So quite often you need multiple compilers and specialized libraries, like, for example, the MPI performance-tuned version on your system. So you need to be very pragmatic about this, especially on HPC system. So the fact that we are working on HPC amplifies what I said earlier even more. And containers, as I mentioned earlier, they help a lot, but do not solve the end platform problem. Yesterday, there was a question about that. I don't remember who asked it, but it's definitely containers do help, but then you would need to build a specific target for each image for each target potentially. For us, so far, we have not done that specifically. We don't see huge performance degradation depending on the system, but eventually at some point, we will move to some more specific images as needed. So SPAC becomes, or SPAC-like system, or SPAC becomes a very important tool in order to package your software and make it available to build complex software task. Understand that yesterday I presented HPSF. This is one of the Linux Foundation project now. And in among those projects, you find some exascale computing program, and SPAC is part of the HPSF initiative. So it's very good because it means that it's not handled by the American labs anymore. They contribute a lot, of course, but it's handled by international association with specific bylaws to support the property aspect of the software. I'm not familiar with GoX HPC, even though we are going to use it in the French NIMPEX initiative, like SPAC. GoX is a similar system as SPAC. It provides a very powerful environment with reproducible builds. And this is also one of the two tools, while SPAC and GoX HPC will be used by NIMPEX to produce the software stack. It answers the similar questions as SPAC, as I mentioned for SPAC. I'm not going to make a tutorial on SPAC here, but I would like to stress a component of SPAC that is suitable for, that is connected to containers and CI/CD. So this feature is actually SPAC environment. So you know, if you have ever used Python you know that in Python, it's a very common pattern to use environments. So in Spack, you can create an environment. It's a YAML file where you can assemble a software stack in order to be able to develop your own application or software. So you have a YAML file that would present that way. So here you define Spack, you define a view of the environment, and then what you want in your environment is a version of OpenMPI 4.16, a version of Boost, the latest, both compiled with the compiler, default compiler GCC. So what you can see here is a glimpse of the language of Spack, which is extremely powerful, I must say. It allows to really provide readable information about the version and the constraints you want to impose on the software. I'm not going to go into this. It would take too much time, but know that it's very powerful and it allows for a lot of flexibility when it comes to building complex software stack. Yeah. So once you have created the file, you can create the environment, a bit like with Python, VM, for example. You can activate the environment, and then once you are there, you can develop. You have access to the entire development to use then Boost and OpenMPI for your own application. So now, how does it work within what we want to build this during this 3 days? So you would create an environment first. That's what you want to do. You create an environment. This is your software stack. Once you created your environment, Spack has a nice containerize command that allows to create, for example, here, a Docker image automatically out of your environment. So basically, you create the environment, your software stack. Spack will handle all this complex dependency graph for you. This is very impressive. It may take some time depending on your software stack, but Spack will handle that, right? Provided that there is a solution to the graph dependency issue. And then it will generate a Docker file for you. So you don't even have to create a Docker file. It's created for you. You have a nice Docker file available. So I put a little bit more complex example here. It's actually a working environment that we use here in the team for a proxy app. You see we have Cocos here for those who know about it. Raja needs Shy and Umpire and maybe Caliper. We want to compile an OpenMP version for Cocos and Raja. Raja and Cocos are frameworks for portable performance on CPU and GPU. And here, what we want to do is use compilers at least GCC, up to GCC 14. So here, when you have the 2 dot here, it means that it's at least 14 up to the latest version. And here, what you see is that we can use Clang between version 14 and version 18 of Clang. You see? So here it's open-ended, and here it's open-closed. So it's up to 18 included. So this is part of the language for the versioning. It's extremely nice. Here, what you see is that we want to have OpenMPI up to version 4. So usually it will take this will take typically the latest OpenMPI version 4, provided that the dependencies here below do not require something less than 4. In that case, it would eventually pick a different version. So this is how powerful this can be. We have some more complex environment here. This is extremely nice, and SPAC automatically takes care of the dependency. Then you give that to SPAC containerize, you have a nice Docker file. Maybe I should comment on this. So the very end, because there was a question, it's a question about the end platform problem. So here what you see at the very end is that we are going to actually build on an Ubuntu 22. So it's either a Docker image where we have installed SPAC or a system which is 2204, sorry. And here's the target. This is very important. Here the target is a generic target. So basically what you will generate is executables that can be run on any of this architecture. But instead of this, you can actually put a more refined, so for example, V2, V3, V4, and you would get then access to more advanced optimization. And you can even have micro architectures. And in that case, you will get specific optimization to the macro architecture of your system. If you do that, of course, you will then build very specific software for the target, for the platform target you want to build the software for. Then you get the Docker image, you can build it, you can check that it's available, you can build the Apptainer image, and that's it. It's as simple as that. The complicated part is, of course, to build properly your SPAC environment. So I strongly suggest that the use of such systems or such workflow, if you don't use SPAC, then use GoXHPC. I'm not familiar with EasyBuild. EasyBuild is a system developed in Germany. Probably EasyBuild has similar features, but I cannot comment on that. I haven't checked what it can do. Once you have your containers, of course, you can do CI/CD automation, and like we will see later today. Okay, that's it for SPAC. Now, we are going to see today a few more jobs in order to complete our pipeline, our workflow pipeline. And a suggestion that we will not implement, but this is as an exercise for you if you are interested in. You can actually factorize your workflow into reusable workflow. So it's called composite action. If you click here, you have access to the documentation of composite action on GitHub. Of course. Yeah. So a composite action will allow you to reuse a specific action in your workflow. So if you have workflows that repeat themselves and to be able to, or jobs that repeat themselves, and you want to reuse them, it may be a good practice to actually create a composite action and then reuse it in order to facilitate the maintenance of your workflows. Because at the end of the day, maybe you have 10, 20, 30 workflows to maintain. And so if you can factor out some common building blocks, then that's great. And it will ease the maintenance. So how does that work? Here we can put the action in this directory. So I create a subdirectory action. This is the name of the composite action that we used. The name of the job we used it yesterday, build or build and test. It's not very important. And then we put a file which contains the action. So it's exactly what we did yesterday, except that we have a new keyword here using composite. And we have here also this new part which describes the action and also which describes input that can take that the action can take. So here the input is called preset, and it will be here before we had default. So we had a preset called default. We could have different presets. So for example, in our case, we use preset in order to define different compilation profiles. So we use that to configure CMake more easily and avoid spending time looking at options for CMake. Everything is factorized inside the preset. So here we would pass the name of the preset. You will see how to pass that in a moment. And then we execute our compilation and test workflow. So how is it called now? So you remember we had this build job. We check out the repository here. And then what we do is that we call our actions like this, and we pass default. So if this is a common operation in your workflow, you can factor it out and reuse it simply like this. Nice. So this allows for consistency, simplification, flexibility. I strongly advise that you look for this kind of thing, especially if you use if you have many workflows, this can become very, very useful. For example, we use that for Apptainer. For Apptainer, we always have the same thing, the way we build the Apptainer images. We definitely use this kind of thing. The next topic is caching and artifact management. So caching, your caching inside a GitHub action is actually very important. It may improve the performances quite a bit if you can afford it. This can speed up significantly the way your workflow runs. So how does it work? Cache is like checkout here. This is an action that is maintained by GitHub because it leverages the GitHub infrastructure. You need to use at least the version v4. Below v4, the versions have been deprecated, so you cannot use them anymore. And what happens here is that you can actually, for example, here what we do is that whatever is in the directory build for a specific runner OS, then we would store the repository build in the cache. That way, the next time when we execute, if we have not made changes to the system, then eventually it won't rebuild anything, or it will rebuild only what is required. So we would gain a huge amount of time. So what is being done here is that runner OS would need to be defined. In our case, it was matrix runs on. It was not runner OS, but matrix runs on. CMake is just, well, this is a CMake build directory that we generate automatically. And here we basically generate a hash tag based on the file CMake list. So we use the file CMake list to generate a hash to make sure that this will be unique, so that the cache is not overwritten by another one. So it would use the content of the top-level CMake list to generate a unique ID. So caching, you see, it's very simple. Just pass the objects that you want to cache, and then next time, first time you would go through it, it would generate this archive, store it, and the time after that, it would download and provide it automatically. And if there was no change to the code, then it would go much, much faster. Artifact management. We saw a little bit yesterday about artifact upload. Now I'll comment on upload and download. So artifacts are very useful. So for example, to provide previews, provide build logs, or testing logs in the workflow execution. So that can be extremely useful. And it's also useful to communicate between jobs. So for example, we use artifacts to communicate resources from one job to the other. I will not talk about that for GitHub. It's a bit more advanced, but it's extremely, there is a very powerful language. There is a powerful language to communicate inside GitHub Action between jobs. So here what we want to do is we use upload artifact, yet another GitHub maintain action. You have to use version 4 because the other ones are deprecated. Again, it leverages the GitHub infrastructure in terms of storage. What we want to do here is store a tarball. This is a tar.gz that we created for our application. So it would generate this. Yesterday, we saw how to add a few other files like license or README. You can also, you can put a list of files, and remember, you need to use a pipe, and then you can use exclamation mark in order to say, no, I don't want this file, for example. Yeah, I will get back to this in the hands-on session. So here, if you have a build tarball as an artifact, you can actually now download it like this and put it in the following path. So here it will download this artifact that we created here. It will download it, and it will download in this directory. So it's up to you to leverage this feature depending on what you want to do. Here are possible, as I mentioned earlier, are possible use cases. We use that a lot to share outputs or resources between different jobs and sometimes workflows. You can store log files, you can debug. Yeah. Actually, I could show quickly a way that we use it. For example, I'm not sure if that will work, but let's see. Yeah, for example, here. So this is a deliverable that we work on for the Exascale project on method and algorithms. So what you see here is a workflow where we have a LaTeX workflow where we verify that we write the deliverable in LaTeX. We have a nice LaTeX template. And here, unfortunately, it expired because I don't want to keep artifacts for too long, because otherwise GitHub complains and I won't be able to store artifacts for some time anymore. But here I could download, if done even a few days after the generation, I could download here this archive, and this archive contains exactly the deliverable plus whatever goes with it. So this is extremely useful, and this is a product of this workflow here, and I check that the archive compiles correctly here. And this is very useful because this archive is then uploaded directly on open science archives, like in France, we have HAL. So we can then upload this automatically and don't have to upload files one by one on this publication systems. So just one example of artifacts. So that's it for caching and artifacts. If you have any questions, please feel free to stop me. Next topic, schedulers. And we will actually use that one. So we will use upload. We won't use download, I think, but we will use upload later. Well, we already used it, and we will use this one also later with the end-zone session. So here I present two scripts. The first one is basically the script that we will be using to submit the job on Carolina. So here, job my app, you see we pass here a CIF image. This is a default name of the image, but if I submit it with a parameter here in the command line, then I would use that one. Remember that to avoid warnings, maybe that's for the Carolina sysadmin, if they could actually add those variables to avoid having the warnings, that would be great. And then we load the modules here, and we can do just srun. So that's it. And you see here, this is absolutely necessary on Carolina, but also on other systems, in order to get the proper performance, MPI performance on node. You don't want to use a networking layer for communication. You want to do in-memory operation for MPI communication when you are inside a node. So this is a critical option here for Apptainer to get the performance that you need. If you don't use that, you will get a big fat warning for each MPI processes that, copy in memory mechanism is not available due to missing user permission. So this is a job, and we will need this script, job monitor. Job monitor is a small script that I developed here, and actually we use something similar for our pipelines on EuroCC system. So what I do here is that I pick the script. I will pass an option here. The first one will be the name of the CIF, the Singularity image. Then I launch the job. So here you see it will be the job that I presented earlier with the name of the image. I would get the job output out of the submission. I would retrieve the job ID, and then I would have a loop here. What I want to do is that inside the workflow, inside the CI/CD system, I would like to wait until the job is finished so that I see what's going on in GitHub Action. So what I do here, I do an infinite loop and I check the job state using the accounting Slurm tool, SACT, looking for the state of the job, and if any of this state is reached, then I go out of the loop. Then this is finished. I show some statistic about the job, and I print also the log of what happened in the container. I could also put the error log, of course, provided here that we don't have any errors. But you could, of course, you can arrange the script to your own will. And in fact, deploying on Carolina will simply be as simple as this. We will use an if statement here. If we are on Carolina, then we will simply launch job monitor with the name of the CIF file, the Apptainer image. So 4 lines here with what we did earlier, 4 lines to actually add to our workflow in order to deploy on Carolina. So we will do that in a moment, starting at 10:30, not 10:30, 11 after the break. So this is as simple as that, and it works great. You need to be aware that depending on the EuroCC system, you may need to adjust the way you do the submission on the machine. So on Carolina, this is great because you have Apptainer on the frontal node, right? So you can submit your job from the frontal using Apptainer. Great. You will see this afternoon a tool that is called Reframe that we use in our FieldPP benchmarking tool. And in that case, it can get a little bit more complicated to deploy on all your PC system because you have basically 2 possibilities. Either everything is available on the front, on the login node, and in that case, it will work like on Carolina as I show here. But if you go, for example, on Meluxina, unfortunately, you don't have access to, for example, to Apptainer locally on the login node. So you need to actually submit a job. You will need to submit the job that would need to submit another job with the proper, for example, for reframe, you will need to submit a job, a reframe job, that would then submit all the benchmarking that you will do. And so it gets a bit more complicated. So here, the procedure will be a little bit different if you work, for example, on Meluxina, because basically you will need to have an extra layer for the submission. But the principle remains the same. Okay, so you see the most complicated part is this script. Well, not that complicated, but still it allows for us to watch what's going on inside the workflow within GitHub on the supercomputer. A few things regarding security best practices. I'm not talking about that here really in details. This is more advanced. You will see a little bit of it in a moment in the hands-on session. We will use secrets, GitHub secrets, one GitHub secrets in order to deploy the Docker images. This is a critical component in your workflows. So we have a lot of secrets in our own workflows, especially API keys, tokens, API keys and tokens, not really password. We have mostly tokens and a few API keys. So for example, we use Girder or CCAN as data management platforms. And so we have in our secrets, GitHub secrets, API keys to access, to provide remote access to data management platforms in our workflows. Remember that if I go there, open in new, let me show it to you again. In this graph here, you have CCAN, Girder, Zenodo. In order to access those guys here in our workflow, we use through orchestration, we use the secrets here that are in GitHub. So the orchestration system know how to discuss with those guys through the GitHub secrets. This is critical. Never write or use something else in your workflows. Never use sensitive information directly. Use secrets. I will show you in the log that you can't see the secrets in the log files. They are hidden. There are other things that may need to be not hard-coded. For example, the project IDs, the logins, and things like that. So we try to hide this information as well. So this is not very complicated. GitHub provide quite a few features in this area. You should leverage this to ensure that your workflows are secured. GitLab has exactly the same type of system for secrets. It works the same. You have a place where you can store API keys, password, or tokens. Regarding performance optimization, you can actually parallelize tasks in a workflow. So you can, and we will see the mechanism that is used by GitHub in order to build the workflows. Matrix builds, we saw that yesterday with the matrix strategy, are very convenient in order to parallelize the build system. So you should identify places where it could be convenient to use this in order to accelerate your pipeline. So sometimes you need to put constraints on your system. There are dependencies. So the language of GitHub Actions allows you to do that. But other times you really want to make sure that things go fast. And so you use, for example, the fact that you may have multiple runners and you use matrix builds in order to execute in parallel in your environment, in your runner environment. Last, well, not last yet, there is still monitoring and logging. A very, very powerful feature, very nice, but powerful, but simple. We will actually create a new workflow called deploy, which will allow us to deploy our code on a supercomputer. So using GH is the command line interface for GitHub. So GH is extremely powerful. I strongly suggest that you get used to it. Personally, I do a lot with it. I automate a lot of tasks. And one thing that you can do is that you can trigger a workflow with GitHub command line interface from your own command line. From GitLab, you could trigger it from GitLab or from GitHub Action. So very powerful as long as, of course, you have the permissions to do so using token, for example. And here what we do, we deploy, we run the deploy workflow on the develop branch of the repository we are in. So if I was in the repository here, in this repository, I would launch this command. It will run if there is a deploy.yml and a develop branch, it will run the deploy workflow. There is no deploy workflow, there is a trigger on YML, but nevertheless, it would run this workflow in the develop branch. Quite simple. So this is very nice because you can, depending on how you work, you may want to deploy an application from script, for example. What we do, how do we use that? It's not exactly like that, but well, for example, the Stereo GUI here, for example, we have a nice application. I didn't put in the screenshot the interface here, but Vincent Chaban, who developed this application, in the GUI, we have a nice deployment configuration for the EuroHPC system. And from our application, we have a nice button, deploy or run, and we can actually run directly from the application on the EuroHPC system, leveraging all the data that has been generated by the application here, and run on the EuroHPC system in an automated way through the CI/CD system. So in our case, the CI/CD system is not directly used in GitHub. It's used through a user application where we can trigger a simulation, complex workflow through GitHub Action and at some point on the EuroHPC system or our own on-premises computing infrastructure. So very powerful stuff. Last but not least, monitoring and logging. So you have a lot of information on GitHub Action. You have the log files. So let me show you here on one repository. So if you click, for example, here, you have a nice summary of the workflow. If you click there, you have access to your log files, right? You see what's going on. And if you click here, you see how much time was done on the job. So you will see a bit more later because we will have more jobs. Later we'll have more jobs, and so you will have more information. So here you would see how your workflow behaves and how much time you spent in each jobs. Yeah. Okay. So this morning it was more like various points to extend what was done up to now. Some of these points, we are going to use them now in the hands-on session. If you have any questions, we have a few minutes before the break, or we can just, go to the break as you wish. So we have a few more questions for 5 minutes, 10 minutes, 5 minutes for Q&A and any questions?
So maybe you mentioned some of the features like parallelizing the tasks or, I don't know, monitoring the tasks. So can you show us maybe some materials for that or some links if you have on
I
top
will show
your
that in
head?
the hands-on.
Okay.
So yeah, I would show you the links for that. I showed you here one with the build here, but we will have more later.
Okay, cool.
We will look at that. Okay. Regarding parallelizing the task, where was that? Here. So a key aspect is actually using the matrix strategy here. So if you remember yesterday, let me go back to So you see, actually, it's quite fast to restart the code space because here they use a caching system. So the images are pre-built. So it's much faster to load the code space than initially. This is quite nice. So if I look here, you remember what we did? So what we can do here, for example, like this, and here like this, right? So I do it quickly. It may not be that great to do that because you see, for each cases, we will reconfigure, rebuild, and retest. So I would do it slightly differently in practice because here the configure build are basically the same, right? So, but anyway, just for testing purposes. So let's go. Let's try this. So what I'm doing here is I'm launching the tests on different configurations. So I will see here the parallelization. It's not a great example again because this is not there are a lot of commonalities, but you can adapt this to a different context if you want. Now I can watch here. So now I have 6 jobs. You see, so we have here the Cartesian product for the matrix, right? So I have I have two jobs here. Why did it fail? Yeah, because we require at least two processes for the application. So that's normal. And why here artifacts tuk. This would be the root. Hmm. Yeah. Okay, I understand. So, yeah, I should have been a bit more careful. So here I will do only 2 and 4, and the artifact here, I need to name it in a unique way. So here I put NP, and then I would have a different artifact here. This, honestly, this is really for demonstration purposes. In practice, what I'm doing here does not make much sense. But anyway, let's see how that works. So what you see is that with those two processes that failed, by default, if there is failure in some jobs, the other jobs will fail also very rapidly. So what we see is that Carolina failed here because we need at least two processes. Wow. And then here, the job was canceled by GitHub because we had failures here. In fact, you can change the configuration of GitHub Action to allow the processes to continue even though you have some failure. So this is an option for the matrix strategy to avoid the workflow to fail if there is a failure. So let's have a look now. Everything is good. Everything is good. We have 2, 4, and they were done in parallel. This is the example here. If I look at there, you see it run on 4 processes. If I look here, it's done on 2 processes. And if I look now here, oops, summary. Yeah. If I look here, you see I have the archive. They are all the same, right? It's just that the archive were generated in different settings. So you see the matrix strategy is actually very powerful. It allows you to launch with different configuration on your system. That's what we use to launch our application on EuroHPC system. I showed that yesterday. In order to do that, we actually leverage matrix strategy, of course. Not only, but this is one of the features that we leverage in order to use this system. That okay?
Yeah, sounds reasonable. Thank you.
Yeah. Okay, then maybe let's have a break. I think it's break time.
Okay, so let's start. Again, I hope everyone had a good lunch. I have put the link to the course in the Zoom chat, and also you can access it from these lectures benchmark in the navigation bar or from here. And a little bit about myself. My name is Javier, and I'm a research engineer in the Semosis team here at Strasbourg in France. And I am currently the lead developer of this framework called FieldPP benchmarking, which is a tool designed to facilitate benchmarking on HPC systems. And well, a little disclaimer, in this course, I will show you how to use, what is FieldPP benchmarking and how to use it. But keep in mind that it is still a young project, a young open source project that is still actively under development. And well, our first release was just done a few weeks ago. And well, feel free to interrupt me if you have any questions. Just can you confirm that you see my screen?
Yes, we can see.
Yes.
Great, thanks. Okay, so this course is entitled Introduction to reframe-hpc and Initial Benchmark Setups. And at the end of the course, you will have learned to, the basics of reframe-hpc and how it is used by FieldPP benchmarking framework. You will have learned how to benchmark a simple application using FieldPP benchmarking and how to visualize the results with the framework. Let's start with an introduction to FieldPP benchmarking. This framework is based on reframe-hpc, and it is designed to automate and facilitate the benchmarking process of actually any application on HPC systems. And one of its main features is that it ensures benchmark reproducibility and allows to have a centralized platform for your benchmarks. You might ask, why would I want to use this framework? Well, for complex applications, benchmarking on HPC systems can be an error-prone process and can become quite overwhelming. So FieldPP benchmarking allows you to run reproducible and consistent benchmarks on different architectures without having to manually handle execution details. Also, well, this tool is adaptable to multiple scenarios. For example, it can help you optimize your code by almost instantly having a comprehensive report. It can help you compare your application on different hardware, and it can ensure non-regression of your software. So in a nutshell, how does it work? Well, to set up a benchmark, you actually need 4 configuration files in JSON format. First, it is a system settings file, and this is actually defined by reframe and describes the system architecture you will run your applications on. So, for example, you specify partitions, environments, and stuff like what's the available physical memory per node, for example. Then you have a machine specification file, and this one actually filters the different environments, specifies how to access a compute node on an HPC cluster, and where to get input data and, well, where to write outputs, for example. Then we have we have a benchmark specification file, and this file actually describes what will be executed, where and how to extract performance variables, and also describes the parameter space that will be used by your benchmark. And finally, we need a figure configuration file. This one will describe what will be shown on the dashboard, the final dashboard containing the benchmarking report. Now, well, once these files are set up, and we'll launch the FieldPP benchmarking tool, a pre-processing stage begins. In this stage, simply, all configuration files are parsed, container images are pulled if needed, and remote file dependencies are downloaded on the HPC system if needed also. And after this, the reframe test pipeline is executed. And well, what happens in this pipeline is that first the parameter space is created. Tests are then dispatched. Multiple tests are created depending on the parameters specified. And it means that roughly there will be one test for every parameter combination, actually the parameter Cartesian space. Then computing resources are set along with a specific scheduler and launcher options. Jobs are submitted by the scheduler. Then performance variables are extracted, and your application is validated using, according to your configuration, using, for example, regular expressions. And finally, there is a cleanup state that will move some files and remove files used by each test. Once this pipeline finishes and all tests are processed, QPP benchmarking will store the reframe reports in a specific folder structure with maybe previous results, previous benchmarks, for it to then render a dashboard containing all available results. And for you can check this little sequence diagram for a little bit more information, and maybe for visual learners to better understand the pipeline. But let's now review what reframe is and what it can do. So in their GitHub page, you can find that reframe is a powerful framework for writing system regression tests and benchmarks, especially targeted to HPC systems. The goal of this framework, as they say, is to abstract away the complexity of the interactions with the system, separating the logic of a test from the low-level details, which pertain to the system configuration setup. This allows users to write portable tests in a declarative way that describes only the test's functionality. So its core features are basically regression testing, that is ensuring that the new changes on an application do not break existing test cases. Then performance evaluation, that is to detect regression and analyze the performance of your application. Then we have performance and sanity checks to ensure, well, correctness and efficiency. And we can now analyze the reframe test execution pipeline. So, okay. So you must know that you can what happens in between these pipeline stages by using Python decorators. So you put, for example, run after setup or run before compile, or as you wish. But the first step of the reframe pipeline is the setup stage. Tests are set up for the current partition and programming environments. What that is by reframe in a minute. And then optionally there is a compilation step. In this step, well, scripts for compiling your application are created and submitted. Is compiled by reframe. Then there is a run stage in which, well, scripts associated with the test execution are created and submitted. When I say scripts, it can be, for example, Slurm scripts or even just simple bash shell scripts. And then we have the sanity phase. This phase the correct execution of the application is validated. And it is followed by the performance stage, where metrics are collected and compared to reference values. And well, finally, there is the cleanup phase. So this image right here shows how a single test is executed for 2 partitions and 2 programming environments. And in here, we have finally a simple reframe pipeline. And we will explain in detail what it does and showcase what it does. Let's do this. Actually, I modified a little bit the pipeline from the one that is on the course content, but roughly it does the same. Okay, so first we see here a Python class called sleep test. It is decorated with a reframed simple test decorator. And it inherits from a run-only regression test from reframe. And well, with these 2 lines, we tell reframe that tests should run on all valid systems and partitions, and on all valid programming environments. These are defined on a configuration file, the system settings. And again, I will show you some examples later in the course. And we have in here a parameter that I have called seconds to sleep. You will understand why in a second. And we use the parameter keyword, and we pass the list containing integers 1, 2, and 3. And actually, reframe will create 3 tests. Each test, in each test, let's say on the first test, this seconds to sleep variable will be equal to 1. On the second test, it will be equal to 2. And on the third one, it will be equal to 3. So now here we will tell reframe what to run. And I have written just a very simple application that actually just sleeps for a number of seconds and actually measures the number of seconds elapsed. So it is just for exemplifying what it can do. And well, after measuring the duration, it will echo slept for X seconds, and finally it will print I'm done sleeping. Note that the application is dependent on the seconds to sleep parameter. So then, using this sanity function decorator, reframe will look for the pattern I'm done sleeping on the standard output, which I tell here. And note that you can actually put regular expressions here. And well, if this pattern is not found on the standard output, the test will be marked as failure. You can actually also do the case where assert not found, for example. So I can put in here, for example, to print error if my application fails, and reframe will ensure that this error pattern does not appear, and if it appears, it will fail. So you can do both. And well, finally, well, you have this performance function. In here, we pass the unit of the performance variable that we want, and I have actually called it sleep time. So by using this decorator performance function and using this method, reframe will extract the number of seconds that the app slept for using this regular expression. Note that in here I have a group, and I tell reframe, okay, look for this pattern, extract this value from the standard output. This value, I tell it by telling it the first group of the regular expression, and parse it as a float. I should have put an integer in here, but it's not important. And finally, this one, we have this set reference method that by just setting the reference attributes with a dictionary looking like this, we tell reframe to compare the extracted value with the parameter value and ensure that it is between a 5% interval. So if this seconds to sleep value, if this sleep time, sorry, the performance variable extracted is outside this interval, the test will fail. So we can execute it to see this. And we see that 3 tests are running for the values 1, 2, and 3. In here, we have the extracted performance variables. For the first test, it is equal to 1. The reference is also 1, and the interval is here. The test passes because it finds the actual output, and we can actually go see the output files that reframe creates. For example, for this test, this is what is run. This is the submission script. Doesn't matter. This is the standard output that reframe catches and parses, so sleep for 2 seconds and done sleeping. And this is the error log, which is empty because there were no errors. And that's it for the reframe pipeline. Do you maybe you have some questions about this? If not, great.
Oh, yeah, sorry, I didn't unmute. I don't know if it's too early, but could you compare this to Jube or Yube? I don't know how to pronounce it probably, from Julish.
Actually, I haven't heard of that.
Actually, this is a similar tool than Yube. In the US, the tool is called Benchmark. You have Yube and you have Reframe. That's the main 3 equivalent tool. I would say that Reframe is a little bit more advanced, looking at the different capabilities. Reframe maybe is a little bit more advanced than Yube or Benchmark in the US. Actually, Reframe is a tool that is being pushed by EuroHPC. No, that's true. But Reframe, the CI/CD we do it ourselves. So actually, regarding Reframe, there might be a few facilities to work with CI/CD, but we don't use it directly. However, Reframe is being pushed by EuroHPC to be used for benchmarking purposes, right? And feature-wise, it's a bit more advanced than the other tools currently.
Okay, thanks.
Okay, so we can now review the reframe system settings file that I talked about that is used to describe the architecture of an HPC cluster. So reframe actually uses this file to specify necessary modules, partition, commands, and environments for your applications to run as you want. And it's either a JSON file or a Python file containing a dictionary like this. And here there is an example of this kind of file, but first I want to show you what for reframe what partitions and programming environments are. So there we go. Reframe actually defines a system as an abstraction of an HPC system that is managed by a workload manager. And a partition is defined by a collection of nodes with similar characteristics. And well, an environment is an abstraction of the environment where a test will run, and you can view it as a collection of environment variables, modules, and compiler definitions. And we have a little example in here that for Carolina, they define two CPU partition consisting of 720 nodes and a two GPU partition with 72 nodes equipped with a GPU accelerator. And for example, a user might define an environment that uses Python 3.8 and another environment that uses Python 3.13. But actually keep in mind that these are reframe definitions. So you can abstract however you like this file. You can create partitions for your own computer. We've just changed the way reframe sees it. Okay, but in here we have a system called my system, and we actually need to define a host name for this system. We can use this get host name built-in Python function for this. Actually, reframe accepts using Python functions like this directly as a string. Pretty cool. Well, this system contains a partition named my partitions that uses a local or node scheduler. I don't remember what is the default value of reframe. And it uses the MPI-Vec launcher. So this partition supports the environment, my environment, that is defined here. And we define that each node of the partition has 4 CPUs, just as an example. And finally, we define my environment, which supports my partition inside my system. So these dependencies might seem a little redundant, but are extremely useful for when we have a ton of partitions and a ton of environments and we want to refactor this file. So it is well taught by reframe, I think. And well, this file can be sometimes quite complex, but luckily the FieldPP benchmarking framework has some built-in files for some HPC systems. So, well, users don't need to create these files and can simply use the built-in ones. But if they want, they can provide a custom configuration. Let's continue. Additional configurations for this file can also be specified, like launcher options, for example, or the available memory per node. And here I've written a file for Carolina. And we can quickly analyze them. So we set the host names as regular expressions, meaning that reframe can be launched either from a head node or a compute node, any of them. We then set a QCPU partition, and actually the actual access to the partition is specified here. And what I was saying before is that the partition being named QCPU does not imply that we will use the QCPU partition from Carolina. It needs to be set up here. We then set the scheduler to Slurm and the launcher to srun. We tell it that we can submit a maximum of 8 jobs at the time, and that each node of the partition has 128 cores, CPUs. Then we can also tell it that this partition has 129 nodes, CPU nodes. Maybe this number might be wrong, just an example. And we tell reframe that Singularity is available, or Apptainer. Actually, it doesn't matter what we use. And finally, we say that each node has 256 gigabytes of available live memory. And we define the default environment that just loads the modules, the OpenMPI and Apptainer module. So that's it for the system settings. And we can go to the next file, which is the machine specifications. This is a little bit different, as this file actually just filters the partitions and environments for a test, can specify input and output base directories that are common for all benchmark applications. So in theory, let's say you have, I don't know, 10 applications that you want to benchmark on Carolina, let's say, on a given system. This file will only exist once. You will only have to create it once, and should be common to all benchmarks. So, for example, this machine I've called a default, and tells reframe to run on my partition and in my environment, and actually tells to write the reframe output directories under the current directory /build/reframe, to write the reports under the current directory reports, and that input data can be found here and outputs should be written here. Okay, maybe this will make a little bit sense later. But before explaining the next configuration files, I want to provide a little example application. So I have in here just an application that sorts a random list, orders a random list of integers using different sorting algorithms. So I believe this is a first good use case for QPP benchmarking, as we can benchmark the time complexity of different algorithms sequentially just to start. And the application takes the number of elements in the list to sort. It takes the algorithm to use for sorting. So I've just written bubble sort, insertion, and merge sort. And it takes as an argument the output file to actually write the execution time, and it will be written in JSON format. Just this, very, very simple. Okay. So now that we have this example, we can pass to the benchmark specification file. And well, this file, the most important one actually, it is used to describe precisely what will be benchmarked and how the test will be parameterized, how to extract performance variables also. And this is the skeleton. Okay, so I have a question that says, can you explain with scenario? Okay, this. Skip, I think. Yeah. So this one here. Actually, this is just a regular expression that's telling reframe that it can connect to any logging 0, 1, 2, 3, or any available nodes, and same for the compute nodes. Maybe, yeah, I don't know if it is clear. And well, for example, if you don't know, this is not a good practice, but if you do not know the host name of the application of the machine, you can use this built-in Python program. Okay. So again, this is the skeleton of the benchmark configuration file. It has a use case name. It has an executable and its options. And it has a timeout so that jobs will be canceled if they take more time than this. It is useful to not waste compute hours on HPC systems if something goes wrong. And then we have the scalability field. In here, we'll specify how to find and extract performance variables. For example, execution time for a given function of your application. And then we have sanity fields in which we pass options to validate the test, and a parameters field that it is used to build the parameter space. So before continuing, I just wanted to know that the framework is equipped with a special placeholder syntax using the double curly braces. And this is used to replace values from a JSON field into another one in the configuration files. And what is cool about this is that it can access runtime values. Like, for example, a parameter value set during the test execution can be accessed by another field in the JSON configuration file. So this is actually what makes the framework so flexible. Okay. So I want to explain the parameters. To set the parameter space where test will be launched, we can fill the parameters field. And in here, for example, we have set a parameter named my parameter that takes the value 1, 2, and 3. So 3 tests will run in total. But reframe, as I said before, it will run the Cartesian product of all parameters that are provided. So, for example, here we have 2 parameters, param 1 and 2, taking the values 1, 2, and A and B, respectively. And that means that reframe will launch 4 tests in total. Well, also, there are some cases where we have a parameter that will take a large amount of values. And well, this framework is equipped with some generators that take care of these use cases. For example, in here we have a generator called geomSpace that will generate the geometric space between 10 and 10,000 using 4 steps, and it is actually equivalent to using the sequence 10, 100, etc. So this can be quite useful for when benchmarking more complex applications. It will actually just reduce the size of your file and the configurations you have to do, and it's better for debugging. And as I said, the actual value taken by a parameter during the test execution can be accessed within another field of the configuration file using the parameters dot the name of the parameter dot value. Now that we have this in mind, we can try to fill to do the previous the example of the sorting algorithms to execute this application. So in here we tell the application to run Python 3 and the machine input dataset based dir value, which is in here. So current directory input data, for example, and /sorting app. So it is a way of refactoring your files. Then we tell that if the application, if the execution takes more than 5 minutes, the jobs should be canceled because it should not take that long. Maybe you know this before. Then we pass the options. The application arguments. In here, parameters are very useful. So the number of elements in the list we want to sort will correspond to a parameter, the elements parameter. So I will say that I want my list to have first 10 elements, then 100, then 1,000, and 10,000. The same for the algorithm. We tell it that first we want bubble, then insertion, and then merge. And finally, for the output directory where we want to write the file, we can refactor it with an output directory field that we have defined beforehand. And we can use this instance keyword that is built in the framework actually to extract the hash code, the unique ID of the test. And this is actually done in order to avoid tests writing on the same file. So just a little trick. I have a question that says if the timeout is passed to Slurm or reframe cancels it. It is passed directly to Slurm. So yeah, it's Slurm that is in charge of canceling the job if the execution takes more than 5 minutes. And users can actually specify the computing resources to run the test, and it can even be parameterized. So in this example, we tell reframe to run the test on 16 tasks, 32, 64, and 128 tasks, with a maximum, taking one node always. And we set the exclusive access to false, and this is actually equivalent to Slurm exclusive directive. Now, how do we extract performance variables? So the scalability field supports this. And you have to specify first a base directory where files containing performance variables can be found. And we tell under stages, here the stages field, to it is a list of performance files, and we can pass a name. Actually, this name will prefix performance variables. It's not relevant at the moment. We tell the file path relative to this directory, the format, current accepted values are JSON and CSV. And if the format is JSON, we should provide a variables path, which is actually either a string or a list of strings, specifying how to find the performance variables inside the JSON. And actually, you can use wildcard syntax to extract values from very deeply nested JSON files and complex JSON files.
You have a question, Javier?
Yes, Michael.
Hi, just a clarification about this. Does this mean that my executable has to produce either a JSON file or a CSV file? Okay.
Yes, at the moment it should do that. In the near future, we want to support parsing the standard output.
Okay.
But yeah, using regular expressions. But yeah, at the moment, there are some constraints. And to continue concerning test validation, what's specified under the sanity field ensures you tell the application the correct way how to check for a correct execution. So it has a success and error fields, and you can pass a list of regular expressions, and reframe will try to find what's under success. And if it's not found, it will fail, and it will, well, check if this is not found in the standard output. And actually, only validating the standard output is supported in the framework right now, but we want to include other files, for example, log files, just raw text files. So finally, in here we have a full example of the benchmarking specification file for the example sorting algorithms application, and I will launch it at the end of the course just to showcase it. And we can go to the final configuration file. This is the figure specification. It contains the necessary information to generate plots that will be displayed on the final report, and actually has a very flexible syntax that allows you to build very customizable figures depending on the parameters you use on your benchmark. So in this example, we can see that we have defined a scatter plot that we have entitled complexity, and only shows the performance, and where the important thing is that the number of elements are put it on the x-axis and the algorithm on the color axis. This is fully customizable, so you can put the algorithm in the x-axis and the elements on the color axis. And what's cool about this is also that you can specify more parameters, and we even support 3D plots, for example, or plots, for example, a parallel coordinates plot where you can pass an arbitrary number of parameters. So actually, this configuration will generate this figure for this use case. So to launch, finally, to launch a benchmark, the field pp benchmarking exec command is in charge of this. It takes the 4 configuration files as arguments. This custom reframe config is optional if the system you want to run on is built in on the framework. And you can actually specify this website flag to automatically render reports, compile them. I mean, I will explain this in a little bit, but compile it and launch and start an HTTP server so you can view your web page, or dashboard web page. And actually, for visualization, we use Antora, which is how this website actually was built. And Antora allows you to write ASCII doc files, and it compiles them to HTML. So
you have a question?
Thank you. Yeah.
Just a couple of questions. So once we define the metrics that we want to extract from either the JSON or CSV file, is this something that you then offload to the reframe pipeline and ends up in the SQLite database or in the JSON? Or is it something that you parse yourself within the field plus benchmarking scripts?
Actually, good question. So I use reframe to extract directly the variables using sanity functions without passing through the SQL database.
Okay, I see. And
so it's kind of on the run. Yeah.
Okay, so yeah, they probably end up as well as in the JSON performance metrics as well in the database. The second question is about the website. Is it bound to Antora, or can one as an endpoint specify any other dashboard reporting tool and then process the data?
It is actually bound to Antora.
Okay.
At the moment, yeah.
Okay.
But once you compile the documentation, the website, you have HTML files which you can then include in your custom dashboard, for example.
Okay, thank you.
So just to show you, I will execute the example that I say. I have all the files here. So my system, my machine specification, my benchmark specifications, and one plot. And I have my application here. So pass these files. And we see that reframe extracts in here execution times for different algorithms. It's kind of hard to see, but we can see, for example, in here, the test for the merge sort with 10,000 elements. And well, in here, reframe has completed the tests. It creates this reframe JSON report, and actually that is the one I parse. Then in here, the files are being generated. The report ASCII doc files are being generated. Antora compiles the documentation, and I start my HTTP server. And I can see here, supercomputers, I have my system, I have my sorting app application, and my use case that I have called sorting, and just my current report. So if I click here, I have all my test cases for the different parameter combinations here, and I have my little figure in here. So I have what is expected for these algorithms. Maybe I chose a bad point scale. Should have taken something linear, but we can see that bubble sort is actually quite has an n squared complexity. So that's actually it for the course. I'm a little bit early also. In the hands-on session, we will actually execute some simple benchmarks on GitHub Codespace and also on Carolina. And again, keep in mind that this framework is still young development, and many features are being added and improved. And also, well, contributions and features, feature requests, and are more than welcome. And well, thank you for your attention. And I'm here if you have any questions or suggestions even. So I have a question that says, can we have a partition as a parameter of the benchmark campaign? Actually, I have considered this. Show you here. You can't right now directly as a parameter in here, like in the benchmark configuration, you can't specify the partition here. However, you can pass multiple partitions in the machine specification file. So in here, partition 2, even partition 3, and these are accessible by the plots. So you can actually generate a plot that compares different partitions. But right now it is bound by the machine configuration, and actually I will change this very soon so that it is modifiable by the benchmarks configuration. So
I had another question.
yeah.
Very often we're in the situation where we build our application with different configuration parameters, and then it's sort of like an execution for each build configuration. Is this currently supported or planned in the future?
It is planned. Actually, right now we do not compile on this framework, but it is planned to add this.
So if I could integrate it in a CI pipeline by adding the builds as Christoph showed us in yesterday and today, and then concatenate this field PP benchmarking step for now.
Absolutely.
Okay.
And it actually supports Apptainer images, so you can use them.
Yeah. Okay.
I have a question that says which of those 4 config files are specific for FeedPP and which are for reframe. And I will show you here. This Python file, the system settings, is specific, reframe specific. So this is reframe that defines it, and actually FieldPP imposes some constraints, like having to specify the number of CPUs, for example, and the rest, the machine, the benchmark, and the figure configuration are from FieldPP benchmarking. And I have another question that says, can you use Pulp with it to monitor parallel efficiency? And I don't know, maybe Christoph could help me answer this question. I'm not familiar.
Actually, I don't know what is Talp. It seems that it's a tool developed by BSC, if I'm correct, but I have no idea what it does and how it does it. So yeah,
Okay.
I would guess that it seems that maybe it wraps some code. Is that correct?
Yeah, it wraps the MPI calls with a library.
Okay.
Yeah, then I would guess then in that case we would capture the output of Tulp instead of our own code, I would guess. Is that correct?
I assume, yeah.
Yeah, so we would capture Tulp outputs, and then that's what we would need to show then. So we could show the output of the application. We still have the log file of the application, but then we would add an extra layer, which would be the talp results. So that would be very interesting, actually. Yeah. Thank you for the idea. So basically, it's kind of a man in the middle, which would be Tulp. And we would just basically have some specific plots generated automatically. Maybe if we say, okay, we use Tulp to run the application, so we would add extra information. Does that make sense? It's not supported yet, of course. I'm just guessing here and just thinking about what could be done.
But actually, yeah, if we are able to capture the output, it is completely possible to do anything we want.
Thank you.
Thank you.
So you could have you could add the you could show maybe the GitHub repository for VPP benchmarking, Javier,
Sure.
and say yeah, you can actually add GitHub issue request for feature there. What you would like to see. So yeah.
Yeah, you
So
can request features in here. I believe we have a contribution guideline somewhere, and
no,
you
the
can
code
create
of
it.
conduct, but
Okay.
we didn't put yet the contribution guideline, neither templates, so it's really open bar here. So feel free to add it here, but it's in the pipeline. I think that would be very interesting. Thank you.
And actually, also you can see. I stop my server. You can see the logs of your application. This is actually the script um, created by reframe under your configurations and the output log. And well, we have the error log also if there are any errors. And actually, you can also specify custom log files for it to capture and show on the report. Maybe I will show that tomorrow in the more advanced settings.
I have a question. If I run the VPP benchmarking a second time, what happens to the dashboard? Does it get overwritten or does it compare the previous and current?
No, actually, very good question. Actually, it creates each report is indexed by a date, and it will add a new report inside each use case that is specified. Maybe wait, maybe I can show some reports in here. So, for example, in Gaia, I have two use. look. Yeah, each time you run it, if you benchmark a different application, it will add it to the dashboard. If you benchmark a different use case, it will add it, and it will create a hierarchy uh, of benchmarks, actually.
I see.
And you have, this is more an advanced configuration, and it's the configuration of the overview plots. You can create aggregations of your reports, and well, compare, for example, different machines. And actually, you when this feature is active, you have in here a button that says overview, and it aggregates all reports that are under this application page.
Mhm.
So here, unfortunately, to show, I have just one report each time. But also, if you are launching the same benchmark over and over again, you can see the evolution on over time of
Nice.
the execution. So you can check for regression tests. I mean, for regression of the application. So
Maybe can you demonstrate it with the example that you executed?
so I don't have one in right now, and as I said, it is a pretty complex configuration. It is a huge file right now that specify each combination. I'm working on making this file more accessible.
But you can show an example, maybe a result
I don't have one in hand.
in bench
Just
PPP, no? You don't have that?
unlucky. I think we recompiled the documentation without this option.
Okay.
Yeah, it's just unlucky.
Okay. Okay. But that's the idea, right? We developed this tool. We had to use reframe, and we didn't want to redo stuff all the time. We wanted to have reproduce to check for reproducibility, and we wanted to have automated reporting being done so that we can send the results to our colleague almost immediately. It's accessible. We can visualize them. And of course, for us, the most important part is checking for regression and verifying over time how it's behaved. So it's a bit more tricky to do, but this is something that has been done. So it seems that we don't have any example here, but in fact, um, this is an important feature for us.
Absolutely. So maybe I can show an example of the file. In here, there are not shown on the website just because I actually forgot an option on the CI. But for example, this plot right here, no, maybe this one. This plot right here will show the date of the report on the x-axis and the execution time on the y, and well, the number of tasks or the computer resource used on the color axis. So it actually corresponds to what we want. I think I have another question that I missed. So another question is there an option to run the same benchmark several times from two to thousands to do statistical analysis on the result? That's an excellent question. It is not currently natively implemented, but there is a workaround of it that I've actually done myself. What I do is that I create a parameter named, I don't know, repeat. And I will set the values, I don't know, just sequence, for example. And you can set 1, just like this, the number of times you want. Actually, you can use a generator. Repeat is a bad name. Repeat run a, a generator called repeat. We say value equals to whatever, just repeat. We set the count to 100. And this will create 100 times the Cartesian product between these parameters. So it will run the same test a number of times. However, then on the plots configuration, the figure configuration, you will have to aggregate the results to compute the average according to this repeat parameter. So tomorrow I will show you how to work with aggregations, but you can do something like this. This is a simple workaround to it, but I actually want to do something more built-in, like just passing an option, for example. So we wouldn't have to worry about all these configurations. So maybe I don't know. Yeah, there's another question.
Yeah, I have a question. Would it be, I guess it's not so easy to, because essentially reframe already on the command line offers many command line options. I guess it's not straightforward to have VPP benchmarking essentially take in the same command line option of reframe and propagate them down. Because for instance, you can pass like additional options like the queue or specific, even the rerun. I think reframe has I guess then you cannot keep track. The VPP benchmarking cannot keep track of these things if you.
Yeah, that's it. Actually, it is easy to propagate the options. However, I was not able to extract the actual averages or the actual statistics of the different runs.
Yeah.
Mm-hmm.
I see. Thank you.
Okay, maybe we can end the session here. And we should do right now a Q&A and a discussion, maybe also including the courses from the morning. I don't know if Christophe is here to take over, or maybe Vincent.
I'm here.
No, thank you. Christophe.
So, are there any questions about what occurred today? We can have a look at the final. I can take a few minutes to show you the final workflow that we worked on this morning, if you like. So, if that's okay with you, I would like to show you the final framework, the final workflow. So you can recover it from my repository here. So let me put it on Slack and the Zoom here on Slack and also in Zoom. Oops. Sorry about that. And I'm looking for the Zoom chat. Yeah. So let's have a look. So here I made a few changes. So what we have first, let me show you the end results. So now if I look at the main branch, now the build Apptainer is done after build Docker. So they are linked both because it's you need to do the first two in order to do the last one. Also, you can have a look here at the at the summary. You have not only the artifacts here. Well, actually, you have the artifacts here, but you actually have a summary of your image, the image that you have generated. You can see here what is the metadata associated with your image. Okay, so this is the end result. And here, actually, what I did is that I added a connection between the two workflows, the previous one and this one. And now we have the deployment of the main branch, which is automatically triggered to deploy the application on Carolina and our workers. So how does that work? So here we modified things a little bit. What did I do? Not much in the CI. I added only one extra step here at the end, deploy. And I used the labels here, the tags, sorry. I used the tag that was used to create the image and to pass it to build Apptainer. So, and I said that build Apptainer needs build Docker. So when you use needs here, needs build Docker, Apptainer will be, build Apptainer will be triggered only after build Docker has been completed. So that's why you see the connection now with the two jobs. But then here we generated some image names, right? So I need to pass that information to the job. And in fact, GitHub Action has a nice communication mechanism between the jobs. And you can actually create outputs. So this is a new thing. You can create outputs associated to a job. And what we want here is that we want to say, okay, I'm creating some output tags. This is my choice. I name it tags. One of the output would be tags, and the tags, it's actually the output of the step called meta. Remember that we actually identify the step, made the step where we define the metadata associated with versioning. We call it meta, so this is meta here. And we look at the outputs of the step meta, and we want to recover tags, which is defined here. So tags will contain the information about the GitHub, the Docker image that we produced. And so now, since we put here needs build Docker, we have actually a way to recover the outputs of build Docker using needs. So when we click on, when we do this, we can actually recover the information from build Docker using this request needs build Docker outputs tags. And that's it. Below, we'll do the same, and we will add the dash sif. Before, what we add here was simply, oops, no. Before, what we had here was coe-hidalgo2 / the name of the repository, and basically what we had was this, right? Was this guy here. So we had this plus the, I don't know, something like this, right? So now it's calculated automatically. It's calculated automatically. And we have a nice CIF file that has been generated and pushed to the GitHub container registry. And then I've added, so I made those changes that allows to pass the name of the image from one job to the other. And the other thing is that I added a new step called deploy. So upon success of the Apptainer job, we have a new image. So what I want to do, for example, is verify that it works fine. And so what I do is that I trigger here. This is a GH, is the GitHub command line interface. It's a very nice tool. It's available on all platforms. It's available with, unfortunately, it's not available here. If you want to make it available, you have to install it. Actually, I installed it earlier, but if you want to install it, you have to do sudo apt install gh, right? So you have to do this. You have to install gh if you want to do it from the command line. And here, no, I don't have. Yeah. So you could actually copy paste the command line here, well, with the proper image name. So you could do it. But you need to use the authentication that we used yesterday with the GSCR_pat token. You need to do that before doing and authenticate through this token. I'm not going to show that. We will use it only through. If you have questions about this, I can answer them later, or we can you can put a request on the forum or on Slack, and I will answer later. So what do we do here? We want to run a workflow on this repository. So when you actually are in the current repository, it's optional because it will find out about the repository anyway. But you can actually trigger a workflow on another, if you have the proper rights, the proper permissions, you can trigger a workflow on another repository. Then we want to run the workflow, which is called deploy.yml. So this is the guy that is here. We want to run it on the main branch, and we want to pass this option here, which is an image, and then we pass the image name. So we would like to run this guy with this option. So you can see the -f as a way to pass options to the workflow. It's kind of a function call, if you like. And then in deploy, so you have to retrieve also deploy, you have to retrieve cy.yml, deploy.yml, and here I've added some options to workflow dispatch. In workflow dispatch, before we had only workflow dispatch, but I added some inputs. So the input is called image. So it's your choice. I mean, I called it image. I put some description here. I say that it's required and that there is a default value, which is basically the image in the main branch. Okay, and this guy, this input can be called here using that construction. So whenever you build an object, kind of a JSON object inside the YML object, you can then access it through this $accolade inputs.image accolade. Right? So basically here we replaced here the image, the Docker image location by the image that we passed to the workflow, and that's it. Afterwards, we create the C file name. It's already it was already built here, and then that's what we execute on the machine. So we change only this to get the proper output, and we added the input here. We could add some other inputs. For example, we say, hey, I want NP. So NP would be the number of processes. It's also required, and by default, it would be 4. And then here, for example, I would add inputs NP, and in job monitor, I would, in job monitor here, I would have the option NPS, NPS, which would be $2, and then here we say it's 4. Right? And then when we launch also here, we would need to pass NPS to the job, and well, then here it will be a little bit more complicated. I'm not sure, I haven't tried that yet, but I would need a way to, of course, modify. I hard-coded the task here, but I could actually control the number of tasks or generate job MPI and generate the job MPI.sh and have the number of tasks. Probably we can do it maybe, yeah, one way would be to generate this file, for example, here, I guess. So, yeah, so that's it. Okay. So I made some small changes. Oh, we can try that one. Except that I haven't changed the code. But as you can see, it's very easy to add some extra configuration. What I'm going to do is I'm going to skip the build for now. Oops. Okay. So skip build. So let me push that. Yeah, okay. So now I have here the changes I made are available here, right? I can check here. You see the job was skipped, so nothing was done. I can actually go to deploy. And now if I look at this, you see I have a small interface, very basic one where I can enter the image. So here, if I do this, it triggers the workflow. Yes, there is another change I've made. I forgot about that one. It's a cosmetic change. So basically what I did is that since you see here, we may have a lot of jobs and deploy, I don't know exactly what it is. So since I have some inputs, I can modify the name of the workflow in order to add some information about the parameterization of the workflow. So I added that. So now let's have a look here. So setup job, we are on Carolina, great. Then we did the checkout, the zip file, then here the Apptainer command, that would be the zip file name. And then we pull the real file here. So we pull the full image with main here, and we execute on Carolina with the job monitor here. So let's try another one. So here I could run and say, instead of main, I could say V2 for example. Except that it does not exist. It's v2.0. I'm sorry about that. We will check later. v2.0. So it's like that. So this one should fail at some point. Yes, it failed. Why? Because the image does not exist. So when you do things by hand, of course, you can make mistakes. Whereas here, this is correct. No. I didn't create. No, there is no V. You see two mistakes. So I need to be careful. There is no V here. So it's 2.0. That's it. Well, now it should be good. Yeah. All right. Great. So we are all good. So we need to be careful about that. So how did I change the name of the workflow? So basically the name remains the same. But here you can have, and you see the, let's say, kind of dynamic name that is built using the input. So here we use again inputs.image in order to know what's going on here. And actually, I could easily add here, for example, $inputs.np. And I will get this, of course. So you can customize the name, and so that you know what you are currently using. So actually, let's commit so that we see the whole framework working. So now what we are going to see is that it starts again with the full workflow. So it's going to build Docker, build Apptainer, and then deploy. And as you could see here, no, not here, as you could see here, nothing has been hard-coded except for oops, where it is? Yeah, except for this. This is the only thing that has been, GHCRIO is hard-coded, and otherwise here, this is totally generic stuff that is being used to generate the name of the package. Yeah. So let's have a look. So we are in build Docker. If you have any question, please ask. I'm not looking at the questions. So let me know if you have any questions. If you try it, then maybe let's have a look. If no, it's in the yeah, maybe everybody's a little bit tired now. So is it? I don't know who's doing it currently, but you need to copy. Yeah. No, seems all right. All right. And deploy. It said here. We are unable to parse. Bon, I need to have a look. Let's go back to mine. Hopefully, I don't have any errors. Still running. Now we are in Apptainer. It's being uploaded. And lastly, yeah, all good. And now you see it run here. So what happens inside the workflow is that there is a token that has been generated automatically for you, and that allows to actually do that operation here. So deploy. So now if we check on the deploy side, it has been already done. You see it now. It has just been changed. You see that we see the new name that we push. So we have 4 here with the image that has been triggered, deployed, and you have the deployment that has been done. So this is a full. So you can check the repository here. It's functional. You can retrieve it. It's public. If you want to do it at home, and if you have any questions, then feel free to ask.
So one question regarding the deploy workflows that failed. So when there was this short error message, so is there any way how to get more information about it? I mean, your repository. Because from it seems like those are quite like.
So what happens here is that you are missing the name. You see, you don't have anything here.
No, it's not. The question is not about this problem. It's about more like your error messages in your workflow that you showed. So it looked like quite short error message, not very descriptive. So the question is if there is any way how to get more information about the error.
In which context?
So if you open your actions and
My deploy script here.
no, I mean in GitLab, and if you
Here?
open one of the failed deployments.
One of my failed deployment. Okay,
Yeah.
here.
And there was this error message.
Yeah. So when you see this, so here you see Carolina has been cancelled because this guy failed. So there is a fast fail trigger. If one of the job fails, the other ones have been, are sent a message to fail also. So that Carolina failed also very quick so that you don't spend time in it.
Sure,
So
but
you know, so that's what it says here. Make
yeah,
sense?
and if you open that,
The other, so this is actually the orchestrator of GitHub Actions that cancels the job automatically. Then the error is actually in this one. So if I look there, what I see is that I made some mistakes here because I put here, you see a V. So I did, I think, a deployment by hand. So I put the V here, so the image does not exist, right? So when you see that the manifest is unknown, it means that Apptainer could not find the image. So the image does not exist. So that's what it says, because here the tag was wrong. I put a V. The next time I removed the V here, and it was all good. Make sense? And the
okay,
same.
so basically this manifest error always refers to some kind of naming issue that it cannot find the file.
It could be a naming issue or just the image. Well, the image does not exist. So
Yeah.
it could be a naming issue or something else, but usually manifest unknown means that the image does not exist. So here in that case, there was a typo here.
Okay, thanks.
So it's convenient, the workflow dispatch, but of course, as you can see, you can make mistakes. Actually, we have a few workflows with many entries here where we can trigger a lot of benchmark directly from the GitHub interface on your HPC system or our own compute system. So this is quite useful. We don't want to make a particular commit whatsoever. This allows to trigger the workflows. So the interface here allows not only for strings, but also multiple choices and as well as Boolean values. And you can check also here, you can select a tag, a branch, whatever you want. I mean, if you do that, yeah. But then in this particular tag, we didn't have the deploy one. So this is good. Any other questions? If not, then maybe a quick wrap up. So this morning, what we saw was a few advanced topic. I pushed for SPAC as a packaging system that solved the software dependency L regarding HPC. It was really developed in this with SPC and scientific computing in mind, and the SPAC environment feature allows you to build a software stack and then containerize it in a very simple way. A single command line allows you to generate from the environment a Docker file. And then the command line that we saw to build Docker images can just be used right away in order to produce a Docker image. You can actually produce also an Apptainer image from a Spack package. You are not obliged to go through Docker. You can actually directly generate an Apptainer image. I didn't show that during my sessions, but there is a specific language for Apptainer images, slightly different from the Docker file, but quite comprehensive. And then we saw various GitHub specific stuff like how to cache, how to deal with artifacts, a few optimization. Yeah, well. Then we almost finished the deployment of code from with totally automatic. So I hope that you appreciate here that from the software to the supercomputer in a totally automated way. This is of course quite nice, I believe, but you need to develop a certain process and understand how to use properly your compute hours on the EuroCC system before doing that, because of course you can use your resources quite easily potentially because you have automated everything. So be careful about that. And then this afternoon, Javier showed you the FieldPP benchmarking framework, an introduction with first reframe. Reframe-hpc is the underlying technology to do the benchmark. In our case, we don't use the compilation part of reframe. We are not really interested in that because our software stack is not compiled with reframe and it would take too much time in our case. So we do not do any benchmarking with respect to compilation options. Here, it could be valuable, but this is not on the radar very soon. However, what you saw is runtime benchmarking, so not compilation benchmarking, but runtime benchmarking, and how to fill the files that are required by reframe. And then you saw how to generate basic benchmarking with FieldPP benchmarking and how to render the benchmarks. And yeah, so that's it. Hopefully it was complete enough. You managed to complete the exercises, or you were close to complete it. You saw hopefully the value of the work. And tomorrow, you will see some more advanced stuff with the benchmarking tomorrow afternoon. And tomorrow morning, Samir will present you the GitLab aspect. So how to do it with GitLab. Thank you very much.
Great. So good morning, everyone. I hope you had you're well rested for today's sessions. We'll take this time in the morning, this half hour, to do a little recap of yesterday, and to answer some questions if there are any. I don't know if you thought of any question during the night. So just a minute. I can really do a recap on Christoph's sessions because I could not attend the whole sessions. But however, I can speak on what we did in the afternoon. So we learned what reframe-hpc was, for those who didn't know, how to build a really simple pipeline with it, and how FieldPP benchmarking actually uses reframe to to execute tests and benchmark applications. So PLPP benchmarking can really be thought of as a sort of wrapper around Reframe, a JSON wrapper that allows users to use JSON files to indicate to Reframe how to execute the tests. And well, actually, also PLPP benchmarking is in charge of the whole visualization. So it takes the Reframe report generated by Reframe, a little redundant, but it takes it, it parses it, and it generates figures according to your configurations, uh, as you say, and it creates a dashboard that is structured to contain multiple applications, multiple machines, multiple use cases. So, and reports that are indexed by a date. So, yeah, as a recap, the 4 configuration files used are the system settings that is proper to Reframe, the machine specifications, in which we tell how to filter tests and where to find some common directories. Then we have the benchmark specifications in which we tell how we will execute the tests. We tell which parameters we'll use, how to extract performance variables, and specific maybe options of your application. And finally, we have the figure configuration. In this one, we specify the figures that will appear on each report. So on the hands-on session, what we did was execute a simple test in GitHub Codespace, a simple sequential test. Then we executed a parallel application on Carolina, a matrix vector product, and we saw actually the speed of the application of the yeah. And well, I believe that's it for the recap on field PP benchmarking. Maybe I see that Christoph is online. I don't know if you're available to do a small recap for your sessions yesterday.
We did it yesterday evening. Anyway, I showed the full deployment from start to finish. So you can play with that. You have access to the repository. We had to change a few things in order to customize communication between jobs in the workflow in order to pass the proper name for the Docker or Apptainer image. We had to customize a little bit also the workflow name because we want to know what is being done in the workflow. So that allows to see immediately what has been run or with what parameters. Also, what we've seen is that it's quite easy to deploy on a supercomputer with a few scripts, and you can check the properties of your code, deploy, check the properties of your code, and actually deploy real applications in a matter of seconds. If you have any questions, feel free. Actually, I have another constraints today because we do have a technical meeting for the COE Hidalgo 2 today, the entire day, and it starts now. So I will have to leave. I will be available on Slack, in the Slack channel. If there are any questions, Javier, or if you need me, I can try to join or answer on Slack at least. I'm really sorry about that. This was agenda conflict. So I have to leave for the day for this technical meeting. I'm looking at the Slack channel. Feel free to ask questions. I will try to come back for the end and mention a few things regarding the environment. So we will actually stop the runners after the course, but the repositories will still be available for you, of course. So you'll be able to retrieve the repository. I believe that you can fork them if you like, but the runners won't be available, and probably we will also remove you from the organization COE Hidalgo 2. However, the repositories are public, so you have access to them, no problem with that. Yeah, so if you want to continue use the environment, you can still do that today. But after tomorrow, things will be shut down regarding the infrastructure. Regarding the last question, let me push a very important feature of those containers. You encapsulate your entire environment inside the container. That's what you do with Docker, right? And so you should have only very minimal dependency over the host system. However, on an HPC system and with Apptainer, what you want to do is you want to make sure that you are properly using the system, right, in terms of performance. So you want to make sure that you use the MPI optimized libraries that are installed on the system. Well, yesterday, someone from, I don't remember, maybe Antoine from Atos, but well, someone made a comment that he managed to get even better performance with the MPI version inside the container. So, well, normally it should be the version outside. Actually, I think, well, it's not I think, I didn't really showed, um, especially, for example, for a machine like Lumi, you need to do some extra configuration to make sure that you have good performances for Apptainer. Uh, but here, at least on Carolina, Discoverer, Meluxina, we get we get similar performances with and without uh, the container. So in our case, use cases, it's all good, right? So Apptainer helps you to leverage properly the HPC components of the host system. That's a big difference with Docker. Docker does not do that.
So I give the floor to you, Samir.
Okay, thank you. Can you hear me properly, everyone?
Yes.
Okay. Then I will share my screen. We have one session where I talk a bit about GitLab and how CI/CD is done through GitLab in some different contexts and in the HPC context, especially how IT4I or Carolina staff members have set it up. So, and then following this, we have like the other sessions, we have a hands-on session where we actually can use the GitLab Runner setup by Carolina, our IT4I, and do some workflows there. So, okay, I will start. Maybe first just a review. Now we've had 2 days of CI/CD and containerization and benchmarking. So basically, where does I suppose you got some. So this is not the official image where you there's like this infinite circle or infinite loop of DevOps. I'm sure most of you have seen this image. So my point here is just that it's a bit, yeah, everyone has somewhat different opinion of what it actually means. So sometimes the test step is the most important. Sometimes it's the release and monitoring. Sometimes one step follows the other. Sometimes some other step follows the other. So basically, the exact order of things is not important, but what's important is the principle that after every code change, this is the principle of CI or continuous integration. After every code change, no matter how small or big, or no matter made by which team. So originally, for example, for web applications, if there's a change in the front end or in the back end, and if they are made a month apart, usually a lot of regressions and the differences in the code between the two teams would get so great that there would always be problems in merging the code. So the basic principle is not that each step is followed exactly or each step comes after one another, but that after every small change, we are sure that our code is still good and the application is still running as well as expected. So yeah, in different applications, different levels of DevOps or CI/CD make sense. So yeah, web applications or security applications, these kinds of applications traditionally, I believe, have more use for CI/CD. For HPC applications, it's a bit different because there is a much bigger difference from CI to CD. For a web application, the CI would be making sure that all of the regression tests are passed, and the CD would be to actually deploy the website. And here it's not so difficult because the environment for the production website can be mirrored very easily. So yeah, so here we have CI, where the earlier basic idea is to run your tests and to catch any regressions as soon as possible. And the team has a good overview of the software status. But for CD, yeah, as I said, for web applications, it's easier, makes more sense. But for HPC applications, because the production environment is not something that you have always in this loop. It's always something that's a bit to the side or a bit special, but you have to have allocation for, have to have access for. And so unless all HPC sites in the future give us an exact replica of the test environment where it's easy to everyone on everyone who is developing locally on their systems to tie this test environment in, which exactly mirrors the production environment. I believe in HPC case, there's not a real continuous deployment or delivery. So it's maybe more discrete deployment or delivery. But through these tools such as GitHub Actions, through containers, through Spec, Easy Build, and Jacquemus CI, we are getting more towards there, but it's not perfect. It's not the CI/CD or DevOps that is in other fields, because they just have it much. The difference between production and development is much more seamless there compared to the HPC world. So yeah, so for some, delivery or deployment means to just.
Okay, so I hope was it okay to get my point between the CI/CD of the cloud world and HPC world? Maybe should I go forward or repeat? Okay, so maybe just to wrap it up, the concept of CD is also maybe different from team to team or from application to application. For some, it's building your application. For some, it's placing this application in a production environment, and for some, it's actually, for example, for Unistar colleagues, it's to benchmark the application on the HPC environment itself. So building the application is their CI, and delivering it to an HPC system and running it there through Slurm is their CD or CB. But again, all these definitions are a bit fluid, and you should use them to help you achieve your goals or to make your life easier, not which I think because of these kind of the buzzword value of them, sometimes they are teams try to just achieve a certain level that they think is maybe it makes sense for one team or application, but maybe it does not make sense for you. Yeah. One more difference is some people continuous delivery is making sure that your application is in the right place, but to actually deploy it, for example, to make the production side change, you need a manual intervention. So that is not continuous deployment. For them, continuous deployment is when this deployment stage is also done automatically. So yeah, we have the building stage can mean different things for different applications. We saw yesterday the MPIC application was built into a tarball, and then later a Docker image, Docker file was built into an image and uploaded to a registry. So yeah, this could be your delivery, or for example, deploying to AWS could be the continuous deployment. One more thing here. So we used the first 2 days we used GitHub Actions and github.com, their runners and their stack, but CI/CD is tool agnostic. So basically could also be done through shell commands or through many other tools like Jenkins, which was previously quite popular. So if in any way that you do your testing, building, and deploying, this is a CI/CD pipeline. It does not have to use GitHub or what we now do, GitLab. Yeah. So maybe I can start now with the overview of GitLab, saying that it's tools agnostic. So we move now from for one session from GitHub to GitLab, and then Javier will take you back to GitHub for the final benchmarking session. So yeah, so both GitLab and GitHub, they use this sort of server client design in their CI/CD. So previously this was not so popular. So Jenkins was did not use this. It would do everything from a central server. But for GitLab and GitHub, things are more distributed. So we have 3 components basically, or 3 major parts, and these parts are always in play together. So we have the GitLab instance, for example, or the GitHub instance, for example, github.com, or which we will see now, and using these exercises, the GitHub provided by IT4I. So everyone should have, as you have access to this training, you should also have an account there. Please let me know if you do not have this account, because unfortunately GitLab does not have this nice classroom feature where all the repositories were automated, and it was a very nice flow for everyone to do their exercises. So here we will go back a bit and do things more manually. So you will need an account in your in the IT4 code.it4i.cz, and we will work from there, make repositories there and work from there. Anyway, so we have this first piece, the GitLab instance. So, and here you store your repository, your code, and also usually this repository will have a workflow YAML file. This is exactly the same as in GitHub. So GitLab has, and also other modern tools like Forgeo and Codeberg, and Woodpecker CI, so sort of everyone is using this kind of design now. So the workflow YAML file contains your instructions, and then you have your so-called runners, which are so yeah, the workflow YAML file can be thought of as basically a series of steps which only has to do with the files or with the code that is stored in your repository. It would, and these steps can be can be a lot of different things, as we saw in the GitHub days. It can be tests, it could be security scans, could be the build or deployment steps or scripts. So basically any kind of manipulation that is done on your code repository files is contained here. And you can think of it as the blueprint or recipe that your CI/CD workflow will follow. And the runners are the programs that actually carry out these steps that we have defined in the workflow YAML file. So here in GitLab, in the GitLab instance, they will take them, take the steps from GitLab and then actually execute them somewhere. So I'm not, maybe it was too fast for some of you to follow, but Christoph showed us sometimes he was using a runner called self Ubuntu, and sometimes he was using Carolina runner. So the self Ubuntu was actually a runner agent that was installed in one of the Unistra machines. And the Carolina runner is installed in Carolina. So yeah, for GitLab, the runners are open source programs, so you can see their source code if you like. They're written in Go, and for GitHub, they are more. For GitHub, it is more common to use the already provided runners by github.com. So sometimes there is a confusion, or there's a when you think of a runner, you think of an entire machine, kind of. This could be a virtual machine or a physical machine. But actually, a runner is just a program that is installed on these machines, and it can have several runner processes going on there. So the important thing is that this agent, wherever it is, on a physical machine or a virtual machine or even in a container or cluster, that it is connected to the proper GitLab instance. So the Carolina runners are connected or registered to the IT4I GitLab instance. And that is why they can take the jobs. I think there is a... Yes, there's a question. We can do this. So one of the actually bonus hands-on, which is a bit difficult to do actually, so I kept it in the end, but we can try to do this. So we can try to install a local runner, but because everyone will be using a different environment, maybe some of you are even on Windows or some Linux, some Mac, it can be a bit not so smooth to do it, but we will try to do it maybe. So yeah, basically it's just a program that anyone, you can see the code and you can host it on your own, or you can use the ones provided to you by a third party. So for example, GitHub or GitLab, but then you have to pay for it as you use their hours. So similar to how you use an HPC system. Yeah. So yeah, one more thing is that, so for example, if you set up your own runner and you link it to one repository of yours, this is a private runner. But runners can also be shared across repositories and shared across projects, groups, or the entire GitLab. So what we will see for Carolina, for IT4I is all of us will have access to the same number of runners because they are shared across the instance. Yes, sorry. One more point also, and a bit of a terminology difference from GitHub is that the GitLab runners have so-called executors. So they have a final part called an executor, and GitHub runners also have something like this, but the GitLab runners are much more customizable. So you can have your runner. For example, your runner is installed on a physical machine, and then it can have a shell executor, which means that it will have access to the shell on this physical machine. Or it could have a Docker executor. So it's set up to have a Docker executor, which means it will not have access to the physical machine itself, but it will launch a Docker container and it will do the CI job in this Docker container. So GitLab also provides virtual machines as executors. You can launch an entire virtual machine from the runner. You can also launch Kubernetes cluster or a collection of pods, run your job there. And as we see, importantly for HPC and also set up by IT4I is the Jacamar CI executor, which is a custom executor. So GitLab also allows you to have custom executors, which you can write these yourselves and achieve different things with them. So Jacamar CI is one such executor, which we'll learn about soon, which is important for the HPC use case. Right. So I hope things are clear here, but to get more feel for it, maybe we will try to set up these runners ourselves as well. Okay, so maybe we can look at this second part of the pipeline, which is this workflow YAML file. So we already had experience with it the last 2 days in the GitHub YAML file. The GitLab one is slightly different, but not too bad. It's not too different, but some of their terms or some of their keywords are different, and this can cause a bit of confusion. So yeah, but basically it is divided into stages. In GitHub, you had just jobs, and there was not like a concept of grouping together jobs. But here in GitLab, you have stages, and in stages you have jobs, basically. And what this allows is, so maybe you remember Christoph was used this needs keyword, so to build a dependency that first this job is completed and then move on to the next job. So this designs makes it a bit easier to see this, because basically the related jobs are put together into a stage, and by default each stage is maybe I should each stage is executed sequentially. So the jobs in one stage are executed in parallel by default. You can also change this using the needs keyword or matrix strategies. But by default, the jobs inside a stage are executed in parallel, but across the stage, they are executed sequentially. So first, your test stage is done. The test jobs are taken out. Then you move on to the build stage. Then you move on to the deploy stage. And so you can manipulate it using different keywords that already a job from the next stage starts when one of the jobs is finished. So you can make dependencies between the jobs. But by default, this is the structure. You have your YAML file, you have stages in your YAML file, and in one stage, you have to put your related jobs together. So it's not like a hard requirement or like a compiler check or anything, but maybe just a best practice or something that makes your YAML file easier to go through if it's getting very big. Things like this. Yeah, so you have the stages, then you have jobs in your stage. The best practice is to have each job just do one task, but this is not necessary. Also because, yeah, often you want to share what you've done with the next job or the tasks of the next job, so you can also bundle them together that you don't have to use caches or artifacts. Yeah, and then each job is made up of different commands, as we saw in the GitHub Actions pipeline. So, I mean, in the end, you could see that a YAML file is basically one long series of like a shell file or like a bash script, where if you did each step manually yourself, you will, maybe it will take very long or can make errors, but you will get, you should get the same result as when a GitLab Runner or GitHub Runner or an agent does these steps. So in principle, it's nothing different from this, but in practice, you can build very large files or complicated files, or yeah, the main thing is that it's automated. So you don't have to do it, but every time you have a change in your code base, all of these steps are executed. And you have a reproducible and automated build and deploy environment. Okay, so we also saw that so in GitHub Actions, we saw that there was an on keyword, and you can specify when you want your workflows to actually run. So you can do this whenever there's a push. So whenever there's a commit and push on the main branch or any branch, you can do this if you want, on a merge request. So it makes sense when there are external merge requests, when you want to check that their code does not interfere with the main code base. And then there are also more complicated triggers, such as launching a workflow after a merge has been made. So it makes, and then also there's something called a merge train, where many different branches are merged together, and the result from there is tested. And so we're not going to that, but at least in GitLab there are, and I suppose probably in GitHub also, there are many different cases where you may or may not want to run your pipelines. And also you can run different kind of pipelines on different kind of triggers. So maybe for some kind of pushes, you don't want to run any pipelines, so you can do this. Maybe you only want to run it on some certain kind of tags. If there are documentation changes, you don't want to run, for example, an HPC pipeline. So yeah, you can. There are different ways to make to set up different pipelines depending on the type of change made in the code base. Okay, so maybe before I go on to apologies for the spelling mistake. So before I go on to the next section, is there any question so far, or has it been clear?
I want to ask a question about where I can get account on the GitLab from IT4I.
Okay, so do you see this link here?
Yes.
Can you try to go to this link? Do you have usually when you get your allocation at Carolina, you also get an account at their GitLab. Can someone from IT4I confirm this?
Actually, I just tried. We got some credential to log in to Carolina, and I use the same on the GitLab, and it's working.
Okay, yeah, I just tried it. Yes, yeah, it works. Thank you.
Okay. So when you log in, do you see this screen, like your home screen, I guess?
Yeah, yeah.
I suppose there are no projects so far.
No projects.
Okay. Okay, very good. That's great. So yeah, so I guess we've come now to Carolina's setup anyway. So as we see, so Carolina, oh no, sorry, IT4I, and they provide their GitLab instance, and so for example, we all have now access there. So that's great. So this is the first part of the GitLab CI/CD is already taken care of. So especially for sensitive applications or maybe where you want the code to be in a trusted place, the one flexibility of GitLab is that you can self-host it. So for example, HLRS has its own GitLab and your organization could also have it. I think GitHub can also be self-hosted, but I think they have some, maybe it's not that easy or somehow I never see, I think it's not free for one thing. So it's not done. It's not usually done. It's not free and also not, in some cases, not open source as it's owned by Microsoft. Anyway, yeah. So we have the first part of our setup, and then Carolina provides us, of course, with the HPC system, but also with the GitLab runners. So basically, we have available 7 system runners, which are running in the login nodes. So 4 are running in Carolina, 2 in Barbara, and 1 in the complementary systems. So maybe the smaller systems or clusters. And then we also have 5 runners in their cloud, so in some virtual machines. And these are don't have access to the system, but have access to this Docker executor that I talked about. So in the hands-on session, we will try and use both these kinds of runners for different jobs. So one aspect of this is that, for example, when you have your own runner, you know that you are using this runner to run your job. But in most cases, we are not exactly we do not exactly pick a runner. What we do is we use tags or these labels from GitHub, such as the runs on label, like Ubuntu latest or Carolina. We use these tags in our jobs, in our CI jobs, and these tags are then matched to the tags of the runners. And it could be, for example, these 4 runners have the same tags, and when our job matches the tags of this type, one of these runners will, or the processes from these runners will pick up our jobs and execute them for us. So in the logs, we can see then which runner and where exactly our jobs are run. But beforehand, we don't have this, usually don't have this ability. I see a raised hand.
Hi, Samir. I have just a question about the runners running on the cloud. How do they then interact with the cluster?
The IT4I cloud runners, I believe, do not interact with the system cluster.
Okay.
They are just they have this Docker executor, and they open a container, and your job is then run in this container.
Okay, so
so if they have a Ubuntu, you give them an Ubuntu image, they will launch an Ubuntu image, and then you can do your job in this image. And then after the job is done, the container is torn down.
So really, like the only way to interact with the Slarm is if the runner is running on either the login node or the compute node. Like there's no other, yeah.
Yes, so at least in this current IT4I setup, it's the only way, I believe.
Okay.
There can be ways in different kinds of systems to do it, but I believe most HPC centers will not do not allow, or so far do not have this kind of bridge between their cloud systems and their clusters.
So
But it is possible to do it. But
I was wondering if that's like one possibility to overcome these issues of security, like if because many systems like don't allow runners on their HPC cluster. So I was wondering if there's a way to have like even a runner running on the GitHub runners, but then interacting with the Slarm cluster somehow.
yes, so in some kinds of designs, which I've seen, where the cloud runners get access, but very isolated access to the system. This can be done, but actually, what we see now here with these system runners, this is quite a secure way to do it, because they used maybe I will. I can talk about it. So they use this custom executor called Jacamar CI, and this it was developed by the ECP project in the US on these national labs, and also worked together with GitLab. So this maybe this would answer, or this would help with the security concerns of most of the HPC centers, because basically what it does is it locks the job to your username. So first of all, it makes sure that the person who runs the job from GitLab is the same person who is the same account on the HPC system. So this I think this is the main concern that most HPC centers have, is that you did not have accountability. You could use maybe a specific account for the runner, and different people could use it. So there was not tying to an account at the HPC center. And also it downscopes everything. So the runner has only user rights. So only what a normal user can do, the runner can do, basically. And then for the user, what it does to makes it easy is that you can interact directly with the schedulers, so like Slurm. So previously we saw Christoph, he used bash scripts to set up the parameters and then to submit this application to Slurm through the GitHub Actions. So not directly in the GitHub action sending it to Slurm, but with Jacamar CI we can do this. And also then this has the benefit that your account is linked to the pipeline, and so you can only run it when you have your permission in the project, when you have your allocation of the node hours is still there. So it seems that a lot of the concerns are solved by Jacamar CI, at least for these major use cases. I'm sorry, I think I see another raised hand from Radim.
Yeah, so I have a question to those runners and executors. So I understand that for like the Docker runners, it's tied to some virtual machines, so it's limited by the resources. But as you said, the runners are just programs. So in case of those like for example, 4 runners on Carolina, why it is limited to the 4 runners?
So these 4 runners, so actually so it's also a bit confusing. Runners are, this program is basically the main agent program, and it can also launch more processes. So one runner can handle many runner processes. One runner agent can handle many runner processes. So maybe if I go to their documentation, we can see the numbers, but I believe maybe 16 or 32 CI jobs can be run in parallel through one runner agent of these 4. Let's see. So we have this is the IT4I official documentation. They introduce CI/CD and their concept here. They also describe a bit the Jacquemart CI. So let's see. So here they've explained their virtual runners. I think so. Maybe it's not written here, but yeah, basically, these 4 runners are they can handle multiple runner processes. So you can think of it maybe like 100 runners going on. But they also it's not that they don't take resources. They also take resources. So it's not a free resource as well.
So is it accounted as like a standard job for the user, or is it?
When you submit a job through the runner, yes. I mean, the runners themselves are just using some CPU and memory, but when they take your job and they submit it to Slurm, for example.
Yeah, the job itself, yeah, but the runner is executed on login, isn't it?
Yes. So so it will not take your HPC resources, but I mean, it will take the login node resources if it's doing, I don't know, if you're building something or downloading things, some things like this. So I think this is like an initial setup from IT4I. So maybe they will also increase this. But having more runners also means more maintenance, because you have to set them up, register them, maybe, as we will see. So
those 4 runners are totally equivalent?
Yes, I believe so.
And the runner can be used at one moment just by one user, or?
No. So this runner, they launch this runner. These are 4 runner agents, kind of. And they can launch multiple runner processes. So this is a bit confusing concept, but basically you can just think of it. They're not this runner can take maybe 16 or 20 different jobs at a time. So it can spawn different processes that are doing it. So, but for convenience sake, because they have the same settings, we also call this runner agent the runner.
So I just got the message through the different channel that there are 4 runners because we have 4 login nodes. So there is probably 1 runner per login node.
Makes sense.
So that's why. And the same for the Barbara because there are 2 login nodes. So that is probably the reason. Okay, thank you.
Okay, so that makes sense. So, but this one runner on the one login node can handle multiple CI jobs, kind of, or can spawn multiple runner processes. I think we have another question.
How does the runner know when the job submitted to Slarm has finished? Does it query like?
I think when it's so Jacquemart CI believes take care of this.
Okay.
It gets the status. Somehow gets the status. I'm not sure exactly how it works, but it somehow gets the status back. And
in this case, because Jacquemart knows about the Slarm, like it has been integrated with Slarm directly, so it knows about the Slarm API or something.
Yes, so it submits the job through SBatch, and then I don't think it polls it through SQ or something, but it gets the results back. So
Okay.
I've only tried it with very small jobs, and then you get the result back.
Okay, thank you.
Excuse me. I have another question regarding this. If the cluster is very busy and your jobs spends a long time in the queue, what about runner times out? Is it handled? Does it start the timer once the job starts? Or does it take also into account the queue? Or I'm curious.
And this is so by default, these runners, I think so far are for small jobs, meant for small jobs. And by default, I think they time out after 1 hour or something. So you can increase this to 24 hours, but then you can risk maybe overusing your own hours or something if something goes wrong in the runner file. So maybe it's doing something unexpected or something like this. So yeah, this is depending on how the system is being used, maybe you have to increase your the job timeout for the runner.
Okay,
So
thanks.
We can see how to adjust this in the settings. Okay. Okay, then if there are no more questions, we can maybe go to the next section where we look at the GitLab YAML syntax and see a bit of the differences between day 1, day 2 GitHub Actions and GitLab. So first, maybe the similarities you've already seen is that this YAML file is in YAML, and it works on the files in your repositories. So, and also you have the same client server sort of setup between the runners and the central GitHub instance. And there are other similarities as well. They both maybe share their designs a fair bit. But there are some key differences. One is that GitHub Actions is quite flexible and popular because of its marketplace, where you saw these actions such as the checkout, Docker push, publish, many different actions that you have. And this was so far not possible in GitLab. So GitLab was quite limited in this regard. They had some, but recently now they started also development here. So they have some components that are officially made by GitLab, but not third-party components. But then I just found actually while preparing for this session that you can also, so there is a way to also now run GitHub Actions inside GitLab pipelines, which is quite weird, but it could. So I haven't tried it, but so I think it has some limitations, such as cannot upload artifacts and things like this. But I believe as this feature is also developed, this was one of the major limitations of GitLab, why people maybe did not use it as much as GitHub Actions. But maybe once this feature is included, it could, on one hand, mean that it's a bit less secure, because third-party actions can have basically what is an action. I just thought to put this in. It's also basically a program or a script, or you can think of it as a function. So just a small program that runs and then destroys itself. It can be based on a container. So the action is just a container which runs some kind of code. Could be anything, shell, Python, or it can be a JavaScript action, which is many of the actions are JavaScript actions. They are faster, but limited to JavaScript. So it's, I think, usually a Node.js application. So if you look into the, most actions have to be open source, so you can look into them, and if you have security concerns. So some HPC centers will not allow that you use external third-party libraries like this, which are made by just some, maybe you do not know the person who makes it, or so you can examine the action, but there is a limit to how much you can examine and the dependencies and stuff. So maybe if GitLab does it in a way where the security is also taken care of, this can solve one of the limitations of GitLab CI. Then another difference is more customized. GitLab is a bit more customizable. So, for example, these custom executors. So I think GitHub Actions does not have a native Kubernetes executor, for example. GitLab also supports SSH, so you can, using a runner, you can SSH into a different system as well. Because maybe of the open source nature of its development, it's more customizable. Also, we saw when Christoph was developing the pipeline yesterday that he had two files, and he could quite easily choose which file to run, or choose both files to run at the same time. And he could also name the file as he wanted. So by default in GitLab, you can change this, but you have this one file, .gitlab CI YAML. And each repository is supposed to have one pipeline. So you can include other files into this file, but this is like your main file, kind of. So it's your main C or something like this. But then GitLab allows quite advanced flows. So it's something called directed graphs, DAGs, where you have dependencies, and then you can launch different jobs or different stages depending on what job is completed. And in this way, you can also launch other workflow files. So you can call different workflow files from within this central workflow file. But these are more advanced concepts. For this default or simple initial version of most repositories, you just have this GitLab CI YAML. Yeah. Yeah. So maybe some links here to, because we are now more familiar with the GitHub syntax. There are two documents, one from GitLab and one from GitHub, that describe how to migrate from one system to the other. So in the exercises, if you want to, during the hands-on session or later on when you, if you're working with both systems or you want to migrate what you learned in the GitHub sessions to GitLab or vice versa, you can use these documents to help a bit. Yeah. But basically, GitLab also has quite substantial document. The main reference for its YAML syntax is this one. And then you have, for example, maybe it has, so for example, it can show you this is a GitHub action YAML, and then it's how its equivalent would look in GitLab YAML. So, I mean, from first glance, it's a YAML, so everything in YAML looks similar, but there are subtle differences which you can get annoying. Okay, so yeah, maybe just the important differences are that we saw this on keyword quite a lot. This is not there in GitLab. Also, we saw this runs on or run keyword. This is also not there. So instead of on, so if you want to say specify it should run only on this branch, GitLab has, actually I should have written here, that has a rules keyword. So you have to do rules and then if CI branch is main, something like this. So GitHub has a nicer syntax here, I think. Then yeah, we have in GitLab stages. GitHub jobs is kind of equivalent, but in GitLab jobs are supposed to be inside stages. Then the environment word is replaced by variables. The runs on is tags. You saw that Christoph carried out individual steps of command line or shell instructions. This is usually combined together in a script tag in GitLab. So you don't have this run steps and then the vertical bar, things like this. Instead of uses, it uses, it has the include keyword. And if you want to launch your job in a container, the GitLab uses the image keyword. Yeah, that's basically it. So, yeah, another difference is how it handles artifacts. So, and also how it handles the checkout. So, in GitHub, you had a distinct checkout action to check out your repository. You don't have this in GitLab. You just have a variable name if you want to check it out or not, because everything is tied to your repository anyway. And then you don't have this upload artifact and download artifact actions, because yeah, up to now you didn't have any actions in GitLab. You just had a keyword that would automatically, in which you could tell you wanted to store some item created in this CI job. And then finally, one more important thing is the secrets management. So for GitHub, you had this, you had a specific section when you went into the settings where Christoph showed that, and he added this token as a secret, and then he could use this secret as a variable in the CI file. So GitLab also has this. It has just basically CI/CD variables, it calls it. And if you want to make something a secret, you have to protect and mask it explicitly. Otherwise, it can come into your logs. So what it says or encourages is to use tools like HashiCorp Vault or external secret management, and it has good integration with them. But yeah, it also has this, the simpler secrets management variables like GitHub has, but it does not call it secrets management, basically, from what I know. So this is kind of it for my for the lecture session. I believe it was to also end at 10:30, or was it to end at 11? I'm not sure. I don't have the timeline. Maybe I can check. If there are questions regarding the material so far.
Yeah, I might have one. As you mentioned, GitHub Actions, that some of them can be used also in GitLab. Does it hold also for Code IT4I GitLab?
So this is quite a new feature. I did not know about this before. So I have not tried it out, but if it works in GitLab, then so this is 17.9.
Okay, so depending on the version on Code IT4I.
It's 17.8. It was also there, but for example, maybe if I go to 16 or 15, I think this was not there. Oh, maybe. Can see maybe it's going a bit crazy. I'm not exactly sure how to go to the older versions, but I'm quite sure it was not there. But I believe so. This is so the IT4I GitLab is quite advanced version, 17.92. So in 17.9 we have this, at least it's in the documentation, so it should be possible.
Thank you.
Okay. One thing also is that the runner version should also match at least the major version of the GitLab instance. Otherwise there can be some, so for example, this new feature, this actions feature would not run in the runner. So we would have to make sure that the runners are also updated as they are discrete components. Yeah. Okay. Are there any other questions so far?
Hi, good afternoon again. So let's start with the next session. And again, thank you, Samir, for this morning's session. It was very instructive and informative. So thanks.
Thank you.
Screen.
Also for your support. Because of the work we did previously, I think it went well.
So let's start this second part of the VLPP benchmarking course. So in this course, in this session, we'll treat more advanced aspects and possible configurations of the framework. So, and again, feel free to interrupt me if you have any questions. I have my chat open. So I will be able to see. Just a little second for setting my setup. Okay, so in this session, you'll hopefully learn to configure FIPP, some common benchmarking challenges, and well, how to customize figures in the dashboard, and also a small overview on how the continuous benchmarking workflow that we use. There are multiple challenges when benchmarking applications on HPC systems. For example, how can one guarantee the reproducibility of the results across different systems? And how can on multiple systems? Also, how this is actually quite a problem. How do we handle benchmarking with large input data sets and in some cases some special memory requirements? So in this session, you'll see how we can to overcome these common issues. As you saw on yesterday's sessions of Christoph, we can use Apptainer to containerize our applications and deploy them on HPC systems. And this way, we ensure that the environment will be the same on every system. However, in the field PP benchmarking context, we need to first tell reframe to allow executing tests with a given container. So it's reframe that actually kind of handles the construction of the Slurm script that will launch the application on the container. And to do so, we need to set these container platforms field under your desired partition in the system settings. Then you need to specify the type of platforms that you want to use. That is Apptainer, for example. And these are the container runtimes supported by reframe. But just keep in mind that FieldPP benchmarking just support currently Singularity and Apptainer. Well, doing this tells FieldPP benchmarking that it is possible to use this container, but not necessarily that it should use it. It just tells it that it's available. And this actually allows you to benchmark applications on different platforms on the same system. And this without needing to modify each time this file. So ideally, this reframe settings file, you only should create it and touch it once. The same with the machine specifications. Once you do this for your system, you should be good to go, and it's just the benchmarking configuration that you should manipulate. So how do we configure these containers on the machine specifications file? So we should tell our benchmarks to run using a given container. So we need to create this containers field. Sorry. And well, this will allow you to specify some common directory paths. For example, where my images are located or where they will be located after handling the pooling. And actually, this container field is a dictionary that contains some key value pairs containing, well, the name of the platform and the associated values. So these values are, for example, also the options field, which will, has options to pass to the container command. For example, we can tell it to bind some directories, but just keep in mind that this options field should only contain machine-related options, meaning that in all your benchmarks that you plan on doing on a given machine, you plan on using this command. I don't know, this, for example, this can be quite common, maybe not the best example, but it is an example of this kind of options. Then we have the cache and temporary directories. And these are actually used to specify custom cache and temporary directories for pulling images. So many Docker and Apptainer, for example, have their own default values for these directories, and these fields allow you to overwrite these values. And additionally, you can specify this executable field, which actually let you set the command used for pulling images. But actually, this field is optional, and field PP benchmarking assumes the pull command from the container name. So in most cases, you can avoid it. There are some specific cases where you should specify it, but not that many. So again, at the moment, we only work with Apptainer and Singularity because we mostly benchmark on HPC machines. Finally, concerning containers, we need to set the benchmark dependent configuration on all platforms. And field PP benchmarking actually has this platforms field, which includes all possible platform configurations that you might want to run a benchmark on. It does not mean that the benchmark will run on every one of them. It's just, the actual execution is told by the machine configuration. I hope you are able to follow this quite bizarre concept. But this is super useful because we might want to benchmark a single application and use case on maybe two different containers, platforms, or in Apptainer and in a version installed in the system. And this syntax, putting it like this, allows you to do this. So we can analyze this example. We have defined an Apptainer platform here, which is, as I said, linked to the machine configuration. And this image here, field, contains the file path where the actual image for the benchmark, the benchmark application can be found, or will be found, because if we specify this URL field, it will pull the image and place it under this file path in here. Then we have this input dir field that actually corresponds to where data is stored inside the container. So in this case, it can be named however you like, because I bind it here to my input directory present on the system. And we also can pass a list of options to the container execution. But in here, try just to set benchmark dependent or application dependent options. For example, this one here, set the number of threads equal to 1. This just depends on a single use case. I do not want in a given HPC system, I might not want to benchmark all my applications using just one thread, for example. And finally, we have this append app option. And I know I'm not very good with naming fields, but this field will actually add options to the application execution inside the container. So I don't know, for example, in the Fibonacci test I showed you yesterday, we could pass in here the number of elements equals to 100, and this allows you to separate. I mean, to use different platforms and different options for different platforms. So maybe for this, you have the built-in platform that corresponds to actually not using a platform or running directly on the system. And actually, you can see that what I was saying, you can add also options to this field. So also, just to finish with this note, you should note that we do not delegate pulling the image to reframe. I know reframe supports pulling images, but actually we do it ourselves to have a little bit more control. And this is done only once, of course, and usually from a logging node. So this way, we do not want to pulling the image to impact the execution and the time taken for our jobs to run. So maybe there are some questions concerning container usage inside the field PP benchmarking. I might not have been very clear on some concepts, maybe. Not, we can continue with handling remote input files that we want. So it is actually possible to download files from a remote location. And this is quite useful when, I mean, input files on the system where benchmarks are going to be executed. So this allows to load them without manually having to code them to copy them from one system to another, and without having to worry that much about their location. So maybe a little motivation about this feature. So some time ago, I was asked to benchmark an application in some EuroHPC system, but I did not have an account, and I was just given a runner, a GitHub runner to do this, and I had no elegant and secure way to upload the input data necessary for the application on the machine. So actually, the machine using GitHub secrets, we had access to this data management platform called Girder. And by implementing this feature, you could easily fix this small issue that I had. However, we should need to be a little bit careful on how to use this feature and where we'll place the data, and maybe don't load too much, because it, I don't know, does not seem like a good practice. But at the moment, just this Girder data management platform is supported. But if at any time you are interested in adding another one, for example, it can even be like GitHub, even if it's not one, or Google Docs, if we can, or a drive. I mean, if we can access an API for it. But now I can explain how this field works. So it's a simple dictionary where you can give an arbitrary name to your input file or a folder. You tell the management platform, the data management platform, you tell if it's a file, an item, for example, a data set, or a folder, as the ID or a way to identify this item inside your remote location. And you just pass a destination to where to download the item in your system. And well, this as well is done usually in a head node, a login node, and you can access the given destination by other fields with this syntax right here. Next. So also, FLPP benchmarking, the framework allows you to specify some input dependencies, I mean, local input dependencies. They can be, for example, well, here you have remote dependencies. You download them in a given destination, and then you can pass this destination to the file dependencies. And what this does is actually, it's very useful to impose validation checks on your input data. So the framework will, before running the benchmarks, will look for all files listed under this field, and will check if they exist, and will fail if some files do not exist. This is, I mean, I believe this is very, very useful, because when you submit, for example, some, I don't know, some Slurm job, sometimes, depending on the application you have, it can be hard to debug if the application, for example, does not complain when there's a file missing. It can be really hard to actually find what's wrong with the execution. We've had this problem where I mean, a file was not being found by one of our applications, and it was taking the default value, and so we had more some strange execution times that were not expected for use case. So this feature allows you to really control this aspect, and also maybe also this field allows you to copy files between different file systems, or even just different directories. And why is it useful? It's because some maybe some HPC systems, well, they have different disks for different purposes. For example, they have a large capacity disks where you store your huge data, and you can have a high performance disk which are optimized for I/O operations. And well, if your data set is too big, you do not want to store it permanently on the high performance disk. So you store it on the large capacity disk, and this field actually depending on this input user gear field will actually copy your data from one disk to another and delete it at the end of the test. So here there's an example of this use case. Let's say, if you remember on the machine configuration, we had this input, the dataset based here. And let's say we set it to high performance disk in some directory called input data. And then we can define this input user dir, which will contain actually the real location of your data. I mean, the real common directory of your data. So it will be in the large on the large storage disk. And if this field is not present, the framework will assume will consider that all your data is already present on this high performance disk. But if you specify it, it will look for files that are under here and will copy them here. So here that's explained. First, the framework will check for input data in here. So this input dependency will check lcd/input data/input file. If it exists, it continues. And right before submission, it will copy this file, preserving actually the whole file, the whole directory structure. So at any case, all files listed under the input file dependencies will be, the existence will be verified. And also you can use parameters in these dependencies. And you'll see on the hands-on session why this is useful. Now let's go to this custom performance variables section. So FieldPP benchmarking has a feature that allows to define custom performance variables based on existing ones, on extracted ones. So this field should be added under the scalability field from the benchmark configuration. And it's actually a list. I can show you, I will show you directly this example. And it's a list containing your defined variables. So in this example, I say, imagine that in here in data.csv file contains these three performance values. So the usual way to extract them will be in here in stages. You pass the file path, data CSV, you'd say CSV format, and it will extract all columns from the file. And actually, if you pass a name, the variables will then be prefixed by this stage one name. And actually, in here in the custom variables, you can define, for example, this total time variable. In columns, I can pass all the columns already prefixed by by the name I chose. We tell it to, well, make a sum of the value of these columns, and you can pass a unit. And this will be accessible on the final report. So this can be useful, for example, if well, you cannot easily modify your application to export some precise value that you want, some precise variable. So you can pass to this to automatically have it on your report. And you can have multiple files defined here, and you can aggregate actually multiple variables from different files. Once they are extracted, they are accessible. And also you can use already, you can use some custom variables to define other ones. So kind of recursion is allowed. Let's go to this next section, which is memory management. You might ask, what would happen if I have an application that I know requires a certain amount of memory? How would the framework know how to dispatch the computing resources according to your memory needs? So you can first specify the available memory per node on your system. This will be on reframe system settings. You can pass, for example, I think on the QCPU partition of Carolina, each node has 256 gigabytes of memory. This value should always be in gigabytes. And is actually defined by field PP benchmarking. So reframe does nothing with this. It's actually the framework, the field PP benchmarking framework, that will treat this value. And then once you have set this, you can, on the benchmarking specifications, you can pass under the resources field the memory that your use case or your benchmark will take your use case, each one of the tests. So you pass it always in gigabytes. And here's an example. So let's say your system has 256 gigabytes of available RAM per node. And each node has 128 CPUs. I mean, you want to run 128 tasks per node. So this configuration will still execute the application on 128 tasks, but it will distribute them on 4 nodes. So 32. So this is under the assumption of your parallel application being correctly, your data being correctly partitioned. Of course, if you're, for example, if your master MPI rank holds all your data, this approach would not work, I think. And a little tip is to specify in here a little bit less of the available memory specified on the documentation of each HPC system. So to avoid having some problems with limited memory. I have a question that says that these flags will be passed to Slurm to dispatch flags. Yeah, exactly. They are passed as Slurm directives. However, I think the memory directive on Slurm is a little bit special. So you have to add some trouble configuring this. So I actually had to compute the necessary resources. I mean, number of nodes, number of CPUs, and I let the Slurm handle how he distributes the tasks, the MPA tasks. But in here we have just hard-coded that our application needs a terabyte of memory. However, we can parameterize this value. An example of this is that we can suppose that we have an application, a mesh, and we want to benchmark 3 different mesh resolutions, for example. And well, each mesh resolution makes the application require different amount of RAM. So in here, half a terabyte, and 2 terabytes. We should create a parameter with these memory values and pass it here to the resources memory field. However, if we just do this, as reframe takes the Cartesian product of all parameters, we will have we will test the M1 resolution with 2 terabytes of memory, and we will add necessary tests that we don't want. So it's kind of zipping to these values, but we can do something like this. We can pass a conditions field to each parameter. So we pass a conditions field to this parameter, and we tell actually for when the mesh parameter takes the value M1, I want to check if the memory parameter takes also the value 512. And if it does not take this value, the test will be skipped. So in here, in total, we will have 3 tests. And I didn't add the other example. But you actually will see on the hands-on session that you can also zip parameters together. So in this case, can be useful, more readable maybe. But there are some cases where the memory depends on 4 different parameters, and you cannot create explicitly define all possible test cases. So this approach can be quite useful. And you see here, maybe it can be a little bit hard to understand without a concrete example, but you see that in here we have a list. So everything that's inside this list will be considered as accepted for the current parameter. So for example, if we have I don't know 1, 2, and 3 in here, the LPP benchmarking framework will check for the M1 parameter when the mesh parameter is equal to M1, it will check if memory is either one of the values in here. And because you can pass also the values for other parameters. So you need to view it as what's inside the list is considered as an OR statement, and what's inside the same. So the same in here. You can pass multiple values. So I have a question that says that do these parameters are unified between Slurm, HTController, and PBS systems? Actually, I have no clue. But reframe, I know reframe supports multiple workload managers. We have conceived the framework to be agnostic of the manager, the scheduler. But there are some cases where there are some features that are only available on that might be only available on Slurm, depending on the directive. If these directives are unified, it's okay. But I don't really know if they are the same. But yeah, for example, there are some features like this, like this memory, where it might just work on Slurm. But in general, you can use any scheduler you want. And we can now pass to how the framework handles the website persistence and how results are aggregated. So, as you know, the framework creates a dashboard. And as we discussed yesterday, we could aggregate the multiple benchmarks together. So, for example, to see the evolution of one use case over time. And also, it is useful to compare different machines or applications together. And I have I have found an example of this. I will show it just after this section. But first, we should understand this website configuration file that I also talked about yesterday. So when a benchmark is done, you've seen that this website config.json is created and located under the reports based directory. So very close to the actual benchmark reframe reports that are exported. So if this file already exists on the given folder, on the given directory, it will just update it with the values taken for the current benchmark. And this file is used to describe the hierarchy of the dashboard. I mean, by the hierarchy, I mean which applications have a benchmark on which HPC systems and which use cases belong to which applications. So each website configuration file corresponds exactly to one dashboard. You can have multiple of these files placed on different locations, aggregating different reports together, generating each one a completely different dashboard with other results. So the structure is kind of simple. I will start with this. Just have a keyword machines, which has the name of the machine in each of the keys of this object, and just a name and a description. The same for applications, with the exception that we can specify something I call main variables that are used for aggregations. And then we have use cases. And in this object, we actually specify which application belongs to which machine and use cases, etc. And finally, where to find all reports for this specific machine application use case combination. So in here, you can actually have a local path like this, which is relative to this, to where this file is located, or can be absolute, doesn't matter. And you can also have remote, using your remote locations. So I actually use this to have a production, sort of production website that I store and make it persist on this data management platform. Because actually we started doing this by committing all files on the GitHub repository, but it quickly became too big. Actually, benchmark results can be quite extensive, and we want to make them persist in order to be able to aggregate them. So how do we aggregate these results? So here I say if our benchmarks contain more than 2 parameters, let's say the number of tasks, the number of elements for a given application, the method used, a solver, a mesh, parameters like this, we won't be able to visualize simply on a simple scatter or line plot, for example, the values taken by the actual performance values. So the framework actually allows you to aggregate the results by reducing the number of dimensions in the data. And also the framework will index each report abstraction based on their date, the system, the platform used, the programming environment used, the application, and the use case. So for this, this is actually specified on the figure configuration. So we can pass an aggregation field that takes to other fields. So column and they describe the column or parameter to aggregate using this aggregation function. So these are actually the available one. You can actually filter also, and this is a concrete example. So imagine you have these parameters, number of tasks, the mesh used, and a solver. So you want to plot the mean execution times based on the task parameter, for example. And to do this, you see that in this plot configuration, I put the mesh on the x-axis and the solver on the secondary axis, which corresponds to this slider here. It's just a picture, so it's not interactive. And then, well, the color axis corresponds to the performance variables for the benchmark. And then I just pass aggregations as a list, and it just takes the tasks parameter and I tell it to perform the mean. So maybe this figure right here, will make it more easy to understand. So in order to generate the figures, I first have what I call a multiple column aggregation possible. You can aggregate columns one after another one. That is possible. Is it the same as multiple columns? I think so. But yeah, if you can do first the mean of the tasks, and then you want to sum the values depending on the mesh level, of filter on the mesh level. Also, I'm sure it will be more clear on the hands-on section. So again, I first have what I call a master data frame that actually contains all performance variables for all benchmarks, for all applications, for all use cases. And that's depending on where I'm located on the dashboard. But when you create a figure, we start by pivoting this data frame. So I put on the first index what you specify on the x-axis. The color axis will always correspond to the columns of the data frame. The values will be in the cells. And I have a multi-index data frame, and the second index, row index, corresponds to the what you pass on the secondary axis field, and the extra axis. Well, you can pass extra parameters, and it will pivot the data frame that way. So you actually, when you do aggregations, you group the values of this data frame and perform an operation on them. So you need to, maybe it's easier to have this data frame in mind when building complex figures. But also, you have the possibility, if you like it, to build, for example, 3D plots if it suits your needs, or some plots that accept more an arbitrary number of parameters, like a sunburst chart, for example. Okay, and about this overview configuration file that actually enables you to aggregate groups of reports together. So for comparing different machines for different benchmarks. And as I said, each performance value is indexed by the performance variable, the variable name, the parameter space, all the parameter combinations. And then we have additional indexes, like the date, for example, the system, the platform, and other things like this. And actually, depending on which level of the dashboard you are, you can access different columns. Sorry, different columns on the figure. So I will actually show right now what this looks like. Maybe okay. So in here, I will take this dashboard contains many benchmarks I've done, and I have chosen the Gaia supercomputer just that is in here in Strasbourg, and just because we have done most of our benchmarks in this machine. And you can see that in here there's a little button that it's called overview that appears, and right now I'm located on the Gaia machine page and I have the applications view in here. So if I click on the overview, I have a figure that compares the execution times of these applications. And actually in here we have just one use case for application, but they will appear colorized in here. So this is an example. Then, I don't know, for example, I can go to this one and I have a ton of reports. In here, I'm in the machine application use case page. So this combination, I know this combination. And we just have the list of reports that are just indexed by the date that correspond to this actual combination. So the overview in here, it will show the total execution time depending on the date that the benchmark was executed. Results might be a little bit weird in here, as I've not taken so much care of this feature. But you can also have, for example, the execution by the environment for the latest benchmark. And I've just done the default environment in here, but can have different bars. So this is an example. And how actually yeah, this is an example of how to generate a plot that will have the date on the x-axis and will show the performance over time of an application. So I don't know, I say color axis is solver, and I will aggregate for the same example as previous. I will aggregate first by taking the mean of the tasks, then the mean of the mesh parameter, and the sum of all performance variables. And this will generate a line plot like the one I just shared. And it is the dashboard administrator that should have the task to define and maintain this overview configuration file. I mean, if I don't know, you are in an organization and want to hold the dashboard with all the benchmarks for this organization, well, you have to configure this file by yourself to tell the framework what should be shown on these overview pages. So also the configuration file is actually too extensive and should be simplified. So this is a feature that we have in mind and we'll work on to improve as soon as possible. But you can actually use it if you don't mind being too verbose. Yes, I see a question.
At this stage, is there anything that prevents me to display results from different machine in the same figure? So very often I'm interested in doing like performance portability reporting.
Yeah. So absolutely. For example, I don't know if I will have a good example in here, but maybe. But in here, I have a benchmarked an application on two machines, on Gaia and Discover. And yeah, not a good example. I don't know what it doesn't work, but if you configure correctly the file, you will have a figure showing this. Mm-hmm.
Okay, thank you.
Of course. Yeah. So I will end this session with a little bit of continuous benchmarking. And also the continuous benchmarking aspect of ULPP benchmarking is not fully automated for all users. So actually, we have built a pipeline. It's not directly available on the package. However, I can show you how it works, and maybe with the previous sessions contents, you can try and eventually replicate it. So you can configure this CD pipeline. Will allow you to centralize benchmark results in a dashboard. You can connect this CD pipeline to a CI or CD. I think it's better CD pipeline. So when you deploy an application, you automatically launch some benchmarks, and you ensure that the application has not regressed, for example. And also you can compare different versions of your application like this. Maybe actually I have here, wait, let me close this. In here we have this repository that corresponds to let's say a dashboard for all
applications under the Kitio namespace, let's say. So you have a dashboard, for example. Right now we have only one application. We'll add more. We have more use cases. And actually, we have set up a continuous deployment, continuous benchmarking pipeline here that I can actually launch it just to test with this workflow dispatch of GitHub Actions. So I choose the main branch. I will run it on Gaia. I want to do Carolina, but unfortunately, I have some missing configurations on my files for this current use case. So I won't, and it's a small test case that I will run that is located inside the repository. And I tell in here just the machines, and I will explain how this works in a minute. So let's run it, hoping that it works. And as I say, this is not directly available, but actually we want to really soon create a template repository containing this pipeline and all the documentation structure, all the dashboard structure are already prepared for you to easily customize it and configure it. So what you need to have is some self-hosted runners on your HPC system that will launch the benchmarks. And we need one default runner that it can even be a GitHub hosted runner that will just be used to dispatch the information on the HPC systems and retrieve all reports and combine them from different machines. So it's basically, it takes the inputs, what I just saw, just a list of the systems I want to run on. It takes the local paths to the configuration files. Sorry. And optionally, it takes an ID of a remote location where you want to directly upload the website for a specific benchmark. So this is if you do not want it to be persistent and you just want to visualize quickly the results, you can pass this. But currently, we just support the geared data management platform at the moment. So okay, once we pass these inputs, we actually have all the machine configurations on a private repository because we believe it's a little bit more secure, and we will fetch this information inside the runner. We then will filter the available systems that you pass, like the list of machine to runs. You filter which configurations you want. Also, we check if runners are available, and if they are not available, well, they are filtered. Then we upload these configuration files as GitHub artifacts. That is to communicate with the HPC systems. On the runners of the HPC systems, these configurations are downloaded from as artifacts also. Then we set up a little Python virtual environment for fieldPP benchmarking to work correctly. Finally, we execute the benchmarks using fieldPP benchmarking exec, depending on the machine. We wait for the benchmark to finish. Then we have our benchmark our reframe reports that are created and uploaded again as artifacts on GitHub Actions. Then on our base runner, they are downloaded and we upload them to our data management platform, but on a specific folder, if you want, that we call staging. This is because we do not want to directly show all benchmarks that we do on a publicly available website like this one, for example. So what happens if if the benchmark fails or there are some results that are inconsistent because of a misconfiguration, we might not want to deploy them. So we have this staging folder and we handle deployment in another way and hopefully unlucky. It's busy, but I can show another example. So in here, it is explained. And the final step, once we have uploaded this on the staging folder, we automatically, a pull request or pull request is automatically created. And this actually allows preview these benchmarks using something called Netlify. So I will show, for example, here we do not have it. But let's say this is an automatically created pull request that states, okay, the benchmarks were done on Carolina and Meluxina for this application, this use case. And Netlify actually has this thing that allows you to preview the results. So it will show a preview of the benchmark, but only the results that are stored on the staging folder. So actually, you will have the choice of when this PR is done, you'll have the choice to either accept it or decline it, and two different things will happen depending on your choice. So if you accept the pull request and merge it, I will start with the other one. If you're not happy with the results on the preview and you close the pull request without merging, all results on the staging folder are moved to the denied folder. And this is a way to use to delete them, but we don't really want to delete some stuff, so we move it to a folder that called denied as a trash can, and we empty it once in a while manually. But if we approve this pull request, what will happen is that we will download all on the base runner. All the results that are on the staging folder will be downloaded. Then we have a production folder containing just stuff we want to see. This is downloaded also. They are combined together. The website configuration files are actually combined together to be included. Then this new production configuration is uploaded, and all reports on the staging folder are moved to production. And well, we deployed we deployed the benchmark, the dashboard using GitHub pages. So these GitHub pages actually will just download the results under the production folder. So it's a shame that this runner is busy, so you cannot see it live. And I think I don't have other runners configured, so maybe there are any questions. So Yeah, I think I covered pretty much everything FieldPP benchmarking can do. Okay, there's a question that says, can you pass arbitrary flags to SBatch like distribution using FieldPP config files? Let me think. Yes, you can, but there's a field called access. You can pass them in there, but maybe it's not the best idea to do this. So a better way would be to have other field that allows you to pass configuration files. I'm sorry, to pass Slurm directives. But you actually can use the access field on the machine configuration for this. Maybe.
Can you expand this? What is this field?
Yeah.
Access field?
Yes, let me show you. Maybe with an example machine. On the example of yesterday's session, it is on the machine configuration file that we specify how to access a given partition and how to pass access for Slurm to know how to use how to launch benchmarks on the compute nodes. So in here, these are directly passed as Slurm directives.
Okay, so it's in the specification of the machine, so it's intended to, let's say, a number of tests, yes?
Yeah, correct. Okay, so maybe before finishing, I can show you some of the plot types that we support. In here, I'm in the documentation of FieldPP benchmarking, and we have these scatter plots, which in here I explain all from the plot configuration, which axes correspond to what in the figure. For example, for scatter plots, this slider corresponds to secondary axis on the plot configuration. Then we have this marked scatter plot that we also can use. The secondary axis corresponds to the mark used. For example, we have some things like a stack bar, a group bar. We can have a heat map in here. It depends on your needs. Show a table, a little sunburst chart. This can be useful depending on the use case. Even parallel coordinates, and we even support 3D plots. They are interactive, so it can be good, again, depending on the use case. And surface plots. So thank you. I think we can, maybe we can do the break a little bit earlier and we continue with the hands-on session. So again, thank you for listening. Thank you for your time. I hope you like the framework and that you can use it with your own applications. And yeah, I'm happy to hear also any suggestions or any feedback on the framework. So yeah, maybe if there are no more questions, I would like to thank you again for your time. I hope you appreciated the session. I hope it was helpful for you. At we have 10 minutes for a final Q&A. It can be general for any course, for this morning sessions also. There's an open discussion and closing remarks.
Thank you very much all, and maybe see you around in Europe.